creating stunning visuals, for a presentation, maybe a logo, even just a quick social media post. It can be a real time suck, right?
Yeah.
Wouldn't it be amazing if you could just, I don't know, just describe what you want and have AI just generate it for you?
Yeah, it's becoming a reality fast. And today we're diving into all of that with OmniGen, a new AI model.
Yeah.
Really making waves in image generation.
We're going deep on this one.
Yep.
Beyond the hype.
Absolutely.
Straight to the source. We're talking the actual OmniGen research paper.
Yeah, get them into it.
By the end of this deep dive, you'll be able to impress all your friends with just how much you know about this tech.
Yeah, and it is a really interesting time for this field because it is evolving so rapidly.
Yeah.
Right now, you often need different AI tools for different tasks. Like you need one for generating images from text, then another one for editing those images, and then another one to get like specific effects.
So it's a bit like having to juggle multiple apps just to like edit a single photo.
Exactly, yeah.
Yeah.
But OmniGen kind of takes a different approach.
Okay.
One that could really change things.
Okay. Okay. So let's unpack this OmniGen thing. What makes it stand out?
Sure.
The paper keeps mentioning a unified model.
Yeah.
Which sounds interesting.
It is. Think of it this way. Instead of having like, a whole toolbox full of tools,
Right.
you have one tool that can handle, a wide range of tasks.
Okay.
That's the beauty of a unified model.
Like a Swiss Army knife for AI image creation.
Exactly. Yeah.
Yeah, I like it. So what are some of the limitations, maybe, of current models that OmniGen with this approach kind of overcomes?
Well, one of the big ones is that current image generators often require like additional modules or adapters to be able to do certain tasks. Like if you want them to make a very specific edit based on your instructions, you might need to, tack something else onto it.
Yeah.
OmniGen, on the other hand, accepts both text and image inputs and in any order.
Okay.
Which really simplifies these processes significantly.
So there's no need to kind of guide it through like a rigid step-by-step process.
Yeah, exactly.
Oh.
It's more akin to how a human brain processes information.
Okay.
Where you can take in different, various inputs sort of simultaneously and understand them in context. And the researcher suggests that this makes OmniGen a lot more flexible and adaptable.
That's fascinating. But let's get to the exciting part.
Sure.
What can OmniGen actually do?
Right.
Make it exciting.
It goes beyond the typical like text to image generation.
Okay.
For instance, there's this thing called subject-driven generation.
Okay.
So imagine you have a photo of your dog, right?
Right.
You could tell OmniGen, put my dog in a chef's hat, and it would ideally handle it all at once.
No more searching for separate images and like painstakingly editing them together.
Yeah, precisely.
Wow.
Figure 6 in the paper shows some really impressive examples of this.
Okay.
And it really highlights how it streamlines the image editing process, making it as easy as just describing what you want.
Yeah.
And it's not just limited to like, putting your dog in a chef's hat.
Right.
It can actually do tasks that you wouldn't typically think of as image generation.
Okay.
Like it can actually deblur images.
Really?
It can identify specific objects in an image and highlight them for you.
So it's kind of blurring the lines between like a creative tool and a more like intelligent assistant almost.
Totally.
Yeah.
Yeah. And figure 8 in the paper, really illustrates this well.
Okay.
It shows how tasks that were traditionally handled by separate computer vision algorithms can now be framed as image generation tasks for OmniGen, which is
interesting.
It's cool. It's a whole new way of thinking about these tools.
It makes you wonder like what this means for the future of creative workflows. Yeah, for sure.
What's going to happen?
Yeah.
But one thing that really caught my eye was the section on emerging capabilities.
Yeah.
What exactly are those?
So this is where OmniGen really starts to, I think, differentiate itself, where it gets really interesting.
Okay.
So what's fascinating is that OmniGen can do things it wasn't explicitly trained to do.
Okay.
So it's learned so much from this, massive data set of text and images that it can now perform tasks beyond its initial programming.
So it's like teaching itself new tricks.
In a way, yeah.
Wow.
For example, the paper describes something called task composition,
Okay.
which means you can give OmniGen multiple instructions at once.
Okay.
So you could say something like, remove this object and then make the image look like a Van Gogh painting.
Wow.
Cool.
And it understands that and can execute those commands, sequentially.
Wow.
And they actually demonstrate this in Figure 10a.
That's incredible. It's like having like this multi-talented artist at your fingertips.
Totally. Yeah.
What other, like, surprises does OmniGen have up its sleeve?
So they also discovered that it can learn from very few examples. So like they showed it just a handful, we're talking like a handful of simple scribble drawings and their corresponding photographic representations.
So they, like, taught it a new visual language, essentially.
Yeah, exactly.
Okay.
And once it had learned this new language, OmniGen could then generate realistic images from completely new scribbles, even if it had never encountered that specific drawing style before.
Interesting.
And they highlight this in Figure 10b.
That's remarkable. It makes you realize just how quickly this technology is, like...
It's moving.
It's moving.
Yeah.
Are there any other examples of these, like, emerging capabilities that really showcase this rapid development?
Yeah, definitely. There's this other really interesting ability. It's called in-context learning, and it's pretty amazing.
Okay.
Imagine, like, there's a really specific object, like something OmniGen hasn't encountered before. Maybe it's like a rare bird species or a unique piece of technology.
So it wouldn't, like, know what it was looking at.
Exactly. But what they found was if you just show OmniGen one example image of that object, it's like something clicks, like a switch flips, and suddenly it can recognize and work with that object in, entirely new images, new contexts. And it's incredibly effective. Figure 10c in the paper really highlights that.
It's like you're just giving it a little nudge, like, in the right direction,
Right.
and then it just, like, takes off from there.
Exactly, yeah.
Wow. Okay, so all of these capabilities are incredibly impressive.
Yeah.
But, the researchers also kind of hint at, like, even more groundbreaking potential.
Yeah.
Especially in the areas of, like, reasoning and something called chain of thought.
Right.
But tell me more about those.
Yeah, so we're already seeing kind of early signs of reasoning abilities in OmniGen.
Okay.
For example, the researchers, they asked it questions about images that required it to understand, like, context.
Okay.
Not just recognize the objects.
Yeah.
So they might show it a picture of a kitchen and ask, where would you wash your hands? Right. And even though the question doesn't explicitly mention a sink, OmniGen is able to, like, identify that as the correct answer.
So it's not just, like, seeing these objects.
Right.
It's actually, like, understanding their purpose and relationships within a scene.
Yeah. That's a big deal.
That's huge.
It is. And that leads us into this idea of chain of thought, or COT.
Okay.
This concept, it's already showing a lot of promise in language models. And essentially what it involves is kind of guiding the AI to break down these complex tasks into, like, smaller, more manageable steps.
So instead of trying to, like, generate, a complex image all at once, it would maybe approach it more like a human artist might.
Totally. Yeah.
Like sketching out the basic composition first and then, like, slowly adding in the details.
Exactly.
Yeah.
And the paper, they touch on, like, some early attempts at applying this COT approach to image generation.
Wow.
And it's, again, still early days,
Yeah.
but the potential is huge.
Wow.
Imagine being able to actually collaborate with an AI art tool, like you're providing input and guidance at each stage of the process.
It's like having, like, an AI partner
Right.
in creativity.
Totally.
It's crazy.
It's exciting stuff.
This deep dive has been incredible.
It's been fun.
We've covered a lot of ground. We're talking understanding OmniGen's, unique unified model. We talked about these incredible emerging capabilities. We even, took a little glimpse into the future with this chain of thought. It's
Right.
a lot. For my final takeaway, what do you think? What's the potential impact? What are we looking at here with OmniGen?
It's clear that OmniGen is, like, a significant leap for AI image generation.
Okay.
It's, it's early.
Yeah.
But the speed at which this is all, developing is astonishing, I think. And I do think that, this research is really pushing the boundaries of what we thought was possible. And I think its impact is going to be felt, across industries, across different creative fields.
Yeah, absolutely. And for our listeners out there, if you are as captivated by this technology as we are, this is really just the beginning. I mean, we encourage you to maybe, go check out the OmniGen research paper, explore this fascinating world a little bit deeper.
Yeah, get into it.
Because, hey, you never know, you might just be the one to unlock the next groundbreaking application.
Oh, that's right. Exactly.
Of this tech. Okay, ready for a peek into the future? You know how we're always talking about AI, right? Well, this deep dive. It's about an AI that's not just writing poems or answering trivia. This one's different. This one's learning like us, but on a whole new level.
It really is fascinating how this research is pushing boundaries.
Yeah.
You know, most AI is stuck in its lane, text, images, you get the idea.
Right.
This is about creating AI that blends understanding of both,
Yes.
which changes the game entirely.
Exactly. Imagine showing a picture to AI and it doesn't just say, oh, that's a cat.
Right.
It understands the context, the humor, even the emotions behind it.
It's true.
That's what this multimodal AI is all about, giving AI multiple ways to sense information,
Right.
just like we do.
What's so intriguing is how it mirrors our own learning process. We don't just read a textbook and call it a day, right?
Right.
We look at diagrams, watch videos, even doodle in the margins to make sense of things.
Totally.
This AI is doing the same, just exponentially faster.
So get this, the research paper we're diving into today is called NVLM, Open Frontier Class Multimodal LLMs.
Okay.
It's from NVIDIA, and for those who don't know, they're basically the rock stars of AI hardware.
Yeah.
They're building the engines that power this stuff.
And what NVIDIA is doing with this research, I mean, it's really pushing the boundaries of what AI can do.
Yeah.
The paper itself is, I will say, pretty technical.
It is, yeah.
But we're here to extract those aha moments for you.
Yes. And let me tell you, the aha moment hits you right away.
Okay.
They start with this figure 1, showcasing what NVLM can do.
Mm-hmm.
And one of the examples, honestly, blew my mind.
Okay.
They fed NVLM handwritten code.
And it understood it.
Not just understood.
Yeah.
It actually translated it into working code. Think about that for a second.
Wow.
Snapping a picture of your scribbled notes and having the AI turn them into a functional program?
Yeah.
That's next level stuff.
It is remarkable.
Yeah.
It hints at a future.
Right.
Where coding becomes more accessible, maybe even intuitive.
Yeah.
Imagine sketching out an app idea on a napkin.
Right.
And your AI partner brings it to life with actual code.
It's mind-blowing to think about the possibilities.
It is.
And this is just one example from the figure.
Oh, wow.
They show how NDLM understands memes, answers questions about real-world images.
Wow.
It's like they're throwing everything at it to see what it can handle.
And that's key here.
Yes.
Previous AI models were like specialists.
Okay.
Good at one thing, but clueless about others.
Right.
NVLM aims to be a generalist,
Okay.
a universal tool that can tackle a wide range of tasks,
Interesting.
just like a human can.
Now, I know what you're thinking. How does it actually work?
Right.
Building an AI like this is like building a super complex machine, right?
Well, yeah.
Well, just like there are different ways to build a car. You've got your sedans, your SUVs, your sports cars. There are different ways to build an AI's brain.
And that's exactly what's being explored in this paper.
Okay.
NVLM experiments with 3 main architectures: decoder only, cross-attention, and a hybrid approach.
Okay.
Each one is like a different blueprint for how the AI processes information,
Interesting.
with its own strengths and weaknesses.
Right. So it's not just about building one AI. It's about figuring out the best way to build it for different tasks.
Yeah.
It's like they're asking which car is going to win this race, and more importantly, WHY.
And this is where it gets really interesting from a research perspective.
Okay.
By rigorously testing these different architectures, NVIDIA is pushing the entire field forward, not just their own work.
It's like they're setting the pace for the whole industry.
Absolutely.
Which is really cool.
Yeah. And one of the things they discovered is that the NVLMX architecture, the one built on cross-attention, is incredibly fast when it comes to processing images.
Okay.
Especially really high-resolution ones.
Interesting.
Which is huge.
Okay.
Because the faster it can process, the faster it can learn.
Makes sense.
Imagine AI devouring information, not in days or hours, but in seconds.
Wow.
That's what this speed allows for.
Yeah, and it's not just about AI sitting in a lab somewhere.
Right.
Think about self-driving cars that need to make split-second decisions based on what they see.
Yeah.
This kind of speed could make all the difference.
Absolutely. Now, speaking of seeing, one thing that really caught my eye in the paper was their emphasis on high-resolution images.
Okay.
You might think, okay, we all want our cat pictures to look good. But for AI, it's more than that.
Right. It's about clarity.
Exactly.
I mean, we've all seen those blurry photos online where you can barely tell what's going on.
Oh, yeah.
Imagine AI trying to read text in one of those. It would be a nightmare.
It would be impossible.
Right.
Precisely.
Yeah.
If an AI is analyzing a street sign, for example.
Right.
A blurry picture could be the difference between understanding the directions and getting totally lost.
Oh, totally, yeah.
So,
And that's where this tiling concept comes in, right?
exactly.
They talk about how NVLM breaks down a large image into smaller, more manageable squares.
Right.
It's like taking a jigsaw puzzle, studying each piece individually, and then putting it all back together to get the full picture.
Exactly.
Right.
It allows the AI to focus on the finer details,
Okay.
which is crucial for accuracy.
Right.
They even have a table in the paper, Table 1,
Okay.
showing how even small changes in how they analyze those individual tiles
Right.
can significantly impact the results.
Interesting.
Yeah.
It's like fine-tuning its vision. Mm-hmm.
Making sure it doesn't miss a single pixel.
Right.
And think about the possibilities. Imagine pointing NVLM at your messy, handwritten notes,
Oh, yeah.
and it could actually decipher them,
Mm-hmm.
maybe even digitize them for you.
It's fascinating to think about, isn't it?
It is.
Now, while we've been talking a lot about images,
Yeah.
remember that NVLM is a multimodal AI.
Right.
It's not just about seeing.
Right.
It's also about understanding and processing language just as well.
Right. It's like being fluent in both pictures and the words.
Yes.
We've all seen examples of AI that can write poetry or compose music,
Mm-hmm.
but then struggle to understand a simple image.
Right.
It's like they specialize in one thing at the expense of everything else.
Precisely. And that's another remarkable aspect of this research.
Oh, yeah.
NVLM isn't just trained on image data.
It's also trained on a massive amount of text data.
Interesting.
It's like studying both art and literature at the same time
Oh, okay.
to develop a well-rounded understanding of the world.
So it's not about being good at one or the other.
Right.
It's about being good at both simultaneously.
Yes.
That's what makes NVLM so different.
Exactly.
Yeah.
And the results speak for themselves.
Okay.
They actually compared NVLM to a purely text-based AI.
Okay.
And guess what they found?
Don't tell me. The multimodal one outperformed it.
It did.
Wow.
In several text-based tasks.
Wow.
The model that had also learned from images
Yeah.
actually did better than the one that had only ever seen text.
You're kidding. That's
That-
incredible. So it's like learning through images actually made it smarter overall, even when it came to understanding language.
That's what the research suggests.
Wow.
And it challenges the traditional thinking
Right.
that AI needs to specialize to excel.
Interesting.
It seems like learning across multiple modalities
Yeah.
might be the key to unlocking a deeper level of understanding.
Okay, now this is where it gets really interesting for me.
Okay.
We're talking about potentially changing how we develop AI in the future.
Yeah.
Instead of building separate AIs for writing, image recognition,
Yeah.
and all these different tasks.
Right.
Right.
We might be moving towards a future where AI is more versatile,
Yes.
more adaptable,
Yeah,
more like us.
exactly. And that brings us to the conclusion of the paper, which I have to say left me with more questions than answers.
Yeah.
In a good way. It really does.
It-
The researchers basically said, if NVLM can do this now, what's next?
Right.
And it really got me thinking,
Yeah.
we've come so far, so fast in AI,
We have.
and this feels like a major turning point.
It's true.
Like, this is a big deal.
If NVLM can already understand images and text with this level of sophistication,
Right.
imagine where we'll be in 5 years, 10 years down the line.
It's crazy.
What problems could we solve?
Yeah.
What amazing things could we create?
It makes you think about the future of, well, everything.
It really does.
Like, if this AI can code from handwritten notes, does that change how we teach computer science?
Oh, interesting.
Does it make programming a skill anyone can pick up, not just a select few?
That's a really good question, and it's one that the research paper doesn't even attempt to answer. This feels like the beginning of something huge.
Yes.
And the possibilities are really wide open.
Exactly. And not just in tech, right? Think about medical diagnoses where AI could analyze images and patient records simultaneously
Right.
to catch things doctors might miss.
It's true.
Or in architecture,
Mm-hmm.
where you could sketch out a building design and the AI could generate a 3D model, taking into account materials, sustainability, all of it.
And let's not forget about creativity.
Oh, right.
Imagine AI collaborating with artists, writers, musicians,
Wow.
not just as tools, but as partners, pushing the boundaries of what's possible in those fields.
It's exciting, but I'll admit a little bit daunting too.
Yeah.
Like, this level of AI could change the workforce as we know it.
It's
Some jobs might become obsolete, sure, but it could also create entirely new industries, new opportunities we can't even imagine yet.
That's why these deep dives are so important. It's not enough to just acknowledge that AI is advancing.
Right.
We need to understand how those advancements work,
Yeah.
what they mean for us,
Yes.
and how we can shape this future, not just react to it.
I completely agree. So listeners, we want to hear from you.
Yeah.
What are your thoughts on NVLM? What future possibilities excite you the most? Or maybe even worry you a bit?
Right.
Head over to our social media and let's keep this conversation going.
Because the future of AI is a conversation we need to have together.
Couldn't have said it better myself. That's it for today's deep dive.
Yes.
Thanks for joining us as we explored the amazing world of NVLM and multimodal AI. Until next time.
All right, welcome back to the deep dive. We're diving into some pretty complex AI stuff today, huh? Diffusion models for geometry estimation doesn't exactly roll off the tongue.
It sounds intimidating, for sure. Although the research claims it's all actually easier than we think.
We love a good challenge here on the deep dive. This particular paper is all about depth, that 3D information our eyes are so good at picking up. This research is all about teaching AI to do the same thing, but with just a single flat image. Like, how do you give a robot depth perception with only one eye?
Yeah, that's a really good way to put it. It's a much harder problem than it seems, right? Our eyes, they work together to create that sense of depth. It's called binocular vision. With just one image, well, AI has to get creative to figure out what's going on in terms of depth.
It's like a tiny object, close up, can look exactly the same as a huge object far away in a photo. How's the AI supposed to know the difference?
That's exactly the challenge. That's what's known as scale distance ambiguity. It's like, imagine trying to draw a detailed map from a single aerial photograph. You can see what's next to what, but good luck figuring out how high those buildings are or how far apart they are.
Okay, yeah, now I see the problem. So how do researchers even begin to tackle this scale distance ambiguity thing? What's the first step?
Well, there's a few different approaches. Some solutions focus on something called relative depth. So it's not the exact distance. It's more like this object is closer than that object. Think of those depth maps you sometimes see where closer objects are brighter. Other approaches, they aim for something called metric depth, the actual distance, in meters or feet. This particular research, though, they're tackling something called a fine invariant depth.
A fine invariant depth. All right, you're going to have to break that one down for me.
Basically, imagine you take that photograph, right? And you stretch it out, or you maybe squash it a bit, even rotate it a little. The relative distances between objects in the photo, they wouldn't really change, would they?
No, I guess not.
So a fine invariant depth, it captures those constant ratios and relationships between the depths. It's not about the actual measurement, it's about the spatial layout.
So it's less about knowing, like, this chair is exactly 2 meters away, and more about knowing, like, the chair is farther away than the table leg in front of it.
That's a great way to put it. And it turns out that kind of information is incredibly valuable for things like, let's say robots navigating a room. You don't necessarily need to know exactly how far away something is, just that it's farther away than the obstacle in front of you.
That makes a lot of sense. But how do they actually teach AI to see depth like that? The paper mentions something called diffusion models, which rings a bell, but I'm a little fuzzy on the details.
Yeah, diffusion models, they're super interesting, and they've really blown up recently, especially for creating images, AI-generated art.
Right, like stable diffusion, that's one of them, right? It can make some crazy realistic stuff.
Exactly. Stable diffusion, that's a perfect example of a diffusion model. And the way they work is kind of wild. Imagine you take a perfectly clear image, and then you just slowly add noise to it, like pixel by pixel, until it's just pure static. That's the diffusion part.
So you're basically watching a photo dissolve into TV static.
Yeah, exactly. But here's where it gets really interesting. These diffusion models, they learn to reverse that process. They start with the static, the noise, and they learn, step by step, how to remove it, to reveal a meaningful image. It's like they figure out how to unscramble that static and find the hidden picture underneath.
That's wild. Okay, but if stable diffusion can create art from noise, how does that translate to, estimating depth?
So there's this other model called Marigold that used a diffusion model similar to stable diffusion, but specifically trained it on depth information. But, and there's always a but, there was a catch with Marigold. It was a real resource hog.
Resource hog, meaning it needed a ton of computing power to work.
Yeah, you got it. It took a lot of processing power to produce those depth maps, and it did all those calculations in multiple steps. Each step, it was like solving a really complex math problem.
So effective, but slow. I'm guessing that's where this new research comes in, right? Did they find a way to make it faster?
Way faster. But the really interesting thing, the how. They actually discovered a pretty major flaw in how Marigold and similar models were actually using this process, like a fundamental error in how they were doing a specific part of it.
A flaw. So it wasn't even about making it more efficient. They actually found a mistake. Okay, now I need to know more about this flaw, a flaw in the system. That's like finding out the navigation app you've been using has a glitch and has been leading you in circles this entire time. So what was wrong? What was the problem with Marigold's approach?
Okay, so you remember how Marigold needed those multiple steps to kind of clean up the image, to denoise it, and figure out the depth? And each step, it was computationally expensive, right?
Like a 7-course meal for your computer's processor. Not exactly a quick snack.
A perfect analogy. So there's this technique, it's called DDIM inference, that researchers use to try to speed up these diffusion models. Think of it like a shortcut. Instead of going through all 7 courses, you just grab a quick bite.
Smart. So instead of all the heavy computation you pick and choose, just focus on the key moments.
Exactly. And here's the catch. It's not just what you calculate, it's also the order in which you do it. Like, think about baking a cake. Yeah. You can't just frost it before you bake it, right?
Oh, yeah. That's a recipe for disaster. You can have a mess on your hands.
Exactly. And that's basically what Marigold was doing. It was trying to, frost the cake before baking it. It was taking information from different stages of the process, the denoising process, but using it in the wrong order, especially when they tried to make it work in just a single step. It's like watching a movie, but just jumping between random scenes. You're never going to follow the plot.
So it wasn't that single-step inference was impossible. It's just that Marigold was trying to do it completely out of order. Like someone skipped reading the instructions.
That's a great way to put it. And that's what the researchers behind this new paper, that's what they cracked. They realized if you fix the order, if you choose the right steps in the DDIM inference, Marigold can actually produce those depth estimations in just one step. Like they found the express lane while everyone else was stuck in a traffic jam.
That's incredible. Do they actually say how much faster it is now?
Oh, yeah, they do. Over 200 times faster. It's a complete game changer, right?
Wow, 200 times. Okay, but it sounds like they didn't stop there, did they? What's this end-to-end fine-tuning all about?
You're right, they didn't stop there. And this is where things get even more interesting because, you see, the researchers, they started to realize this flaw with DDIM, it was just the tip of the iceberg. It made them question a lot of the assumptions that were being made about how to train these diffusion models for depth estimation in the first place.
Okay, now you have to tell me assumptions like what? Like what kind of assumptions?
Well, before this, everyone just assumed you needed these incredibly complex training setups to get these diffusion models to work for something as hard as depth estimation. Like these really elaborate multi-stage training processes. It was like putting the AI through years of school before you even let it try the real thing.
Okay, so it was a super compartmentalized approach. Train this part, then try to put it all together.
Exactly. And what this research shows is that, well, maybe that's way too complicated. They propose a much simpler approach called end-to-end fine-tuning.
All right. I like the sound of simpler, but break it down for me. What is end-to-end in this context?
So basically, they take the whole diffusion model, even the parts that had already been trained on massive data sets like stable diffusion, and they just fine-tuned it directly on the task of depth estimation. No more separate training. It's just all in learning together from the start.
So it's like instead of teaching each part in isolation, you're treating the whole model like one big system.
Exactly. And to make things even simpler, they simplified the guidance they gave the model during training. It's like, imagine trying to teach someone to bake, but giving them a million different rules and restrictions. It's overwhelming, right? Instead, they just use this one super specific targeted signal, it's called a loss function, that basically tells the model, hey, this is how close you are to getting the depth right.
Wow. And that actually worked. I mean, it seems almost too simple. Like the answer was right there in front of everyone the whole time.
Right. Sometimes the most elegant solution is the simplest. And here's the thing. The results speak for themselves. This much more straightforward end-to-end fine-tuning, combined with the fix for the DDIM inference, it actually outperformed the more complex methods.
No way. So they made it faster and more accurate just by making it simpler? That's amazing.
It is pretty remarkable, right? And the best part, they didn't even need to start from scratch. They were getting these state-of-the-art results using models like Stable Diffusion, which, it's readily available.
That is a game changer. It's like finding out you can cook a gourmet meal with just a few ingredients in a microwave. But before we get too carried away with all this, what does this actually mean for the real world? Like, what are the actual implications of all of this? This is huge.
Yeah.
But I think it's easy to get a little lost in the weeds with all the technical stuff. What does any of this actually mean in the real world?
Well, think about it this way. This means high-quality depth perception in AI is suddenly a whole lot more accessible.
Okay, I like the sound of that. But accessible how?
Well, think about all the fields that rely on being able to understand the 3D world, but from 2D images.
Okay, so we're talking robotics, self-driving cars, augmented reality. Like, it's a pretty big deal for a lot of different fields.
Exactly. And before this research, to use this kind of tech, you either needed like a supercomputer,
Right.
or you just had to live with results that weren't as accurate. This could change everything.
It's like a real game changer for smaller companies, or even individual researchers who want to do cutting-edge stuff but don't have unlimited resources.
Right. It opens up so many new possibilities. Imagine a future where robots can navigate like really complex environments, not because they have these massive brains, but because they're using these really elegant algorithms.
Yeah. Instead of giving a robot bulky, expensive hardware, you give it better software. It's like giving them a sixth sense. And what about applications for AR and VR? I feel like those are areas that are always pushing the limits of what's computationally possible.
Absolutely. I mean, if you want AR and VR to feel real, to be immersive, you need really good depth perception, right? This research could be what unlocks all that potential we keep hearing about.
You know, more clunky headsets or laggy graphics or any of that. It could be huge. And I think what's really exciting here is that it's not just about doing something faster. It's about being able to do things that we just couldn't do before.
And you know what else is exciting? This whole idea of end-to-end fine-tuning, of taking these powerful diffusion models that already exist and adapting them for very specific tasks. I think this could revolutionize way more than just depth estimation.
So you're saying this isn't just about AI learning to see better. It's about completely changing how we even think about AI development.
Exactly. I think this research is a really good reminder that sometimes the biggest breakthroughs come from challenging assumptions and finding a more elegant, simpler solution. We often think more complexity equals better results, but maybe that's not always true.
It's a good lesson. Sometimes the best solution really is the simplest one. So any final thoughts for our listeners today? Anything to keep them pondering this whole idea of elegant solutions?
Well, the question that's been on my mind is, if simple fine-tuning can be this effective for something like depth estimation, what other complex problems might have surprisingly simple solutions just waiting to be found? It's something to think about.
I love it. A little AI mystery to keep everyone on their toes. Well, this has been fascinating. Thanks for joining me on this deep dive. This research has really changed how I think about the power of simple solutions. Until next time, keep exploring.
Ever wish you could just like build these entire 3D worlds by just describing them? Like you could just tell a computer, I want a cozy cabin in the woods, and poof, there it is, ready to explore.
Right.
Well, we're diving into this world today, the world of AI that's making this a reality, and it is seriously cool stuff.
Yeah, it's not science fiction anymore. We're seeing these incredible leaps in AI and 3D modeling, and it's like the lines are starting to blur between like imagination and digital creation. It's really cool.
We're taking a deep dive into something called Phidias today.
Okay.
It's this new AI model that's turning heads because it's not just generating random shapes.
Right.
It's using references, kind of like how a human artist might use a picture or a model to guide their work.
Yeah.
We're looking at excerpts from their research paper, and trust me, you don't need to be a tech whiz to appreciate what they've accomplished.
It's so fascinating because like Phidias is really designed to make 3D modeling accessible to like basically anyone.
Yeah.
I mean, traditionally, if you wanted to create something in 3D, you needed like specialized software and a lot of technical skills.
Yeah.
But Phidias really changes all that by letting you use simple text prompts, images, or even like existing 3D models as starting points.
That's right.
Yeah.
The paper is titled Phidias, a generative model for creating 3D content from text, image, and 3D conditions with reference-augmented diffusion.
Right.
Yeah.
It's a mouthful.
It's a bit of a mouthful.
But the important takeaway is just that Phidias is so versatile. You can feed it different kinds of creative input, and it just gets it.
Yeah, and to see it in action is pretty mind-blowing.
Yeah.
Figure 1 from the paper shows just how detailed these models can be. There are chairs, cars, animals, you name it. Phidias can probably create it.
Right.
And get this, the caption mentions that the references can be retrieved.
That's a crucial detail.
Yeah.
Because it means Phidias can potentially search like this massive online library of 3D models to find that perfect reference for whatever you put in for your prompt.
Wow.
So let's say you want a vintage lamp for your virtual living room. Phidias could potentially sift through millions of models
Wow.
to find just the right one
Yeah.
and use that as inspiration to build exactly what you've described.
Okay, so we've established that Phidias is a game changer in
Definitely.
terms of accessibility and the sheer variety of what it can create. But what makes it better than like previous attempts at AI-powered 3D modeling?
So previous models really struggled to create consistent high-quality models from just like a single image or a text description.
Right.
They might give you like a rough approximation of a cat, but it might be missing a leg or have like weird proportions.
So not exactly the majestic feline you were hoping for.
Right.
I've been there with those AI image generators
Right.
sometimes. It's hilariously bad.
Exactly.
Yeah.
But Phidias tackles these limitations head-on by using 3D references. Think of it like this. If you were trying to draw a horse, would you rather start with a blank page or a basic outline to kind of guide you?
The outline for sure. It gives you a framework to build on.
Exactly.
Yeah.
And that's what the 3D reference is providing for Phidias. It's like giving the AI a more detailed blueprint, which leads to much higher quality and more realistic models.
That makes a lot of sense. So
Yeah.
it's not just randomly throwing sheets together anymore. It's using like a more intelligent approach to understanding the structure and form of what it's building.
Right.
But how does it actually work? There must be some serious tech wizardry happening behind the scenes.
Absolutely. There are 3 key innovations that really set Phidias apart. The first one is called Meta Control Net. Now, I know that sounds
A
complicated.
little bit, yeah.
Yeah.
Like something out of a sci-fi movie.
It does, right. But you can think of Meta Control Net like the conductor of an orchestra. It's controlling how much influence that reference model has at each step of the creation process, making sure everything's working together harmoniously. Sometimes the reference and the user's input might not perfectly align, so Meta Control Net makes sure that the final model doesn't end up looking like a jumbled mess.
Okay, so Meta Control Net is like the quality control manager, making sure everything stays in track.
Exactly.
What about the other 2 innovations?
All right, so the second one is called dynamic reference routing. And essentially what that means is Phidias uses different levels of detail from that reference model depending on what stage of the creation process it's in.
So kind of like how an artist might start with a rough sketch and then gradually add more and more detail until they have the finished masterpiece.
Got it.
Okay.
And then finally, there's self-reference augmentation, which is where things get really meta.
Okay.
Basically, during its training process, Phidias learns by using itself as a reference, but with slight variations.
Hold on, it's learning by looking at its own creations. That's like next level AI right there.
It is. It's wild. And that's a big part of why Phidias is so good at what it does. By constantly practicing and refining its skills, it gets better and better at generating realistic and creative 3D models.
Mhm.
You know, it's like that friend who's always sketching and experimenting with new art styles. They just keep getting better with practice.
That's a great way to put it.
Right.
But, as much as I'm like loving the potential here,
Yeah.
I have to imagine there's still some limitations to what Phidias can do.
Yeah, you're right to be thinking that way. Even with all these advancements, there are still challenges to overcome.
Yeah.
One of the biggest is that Phidias's performance is directly tied to the quality of the 3D reference database it has access to.
So if Phidias's mental library of models is lacking in a certain area, it's going to have a harder time creating something new and unique in that category.
It's exactly. The researchers are working on expanding the database, but it's a work in progress.
Okay, we're back and ready to like keep this train rolling. We've talked about how Phidias is like pushing the boundaries of what's possible with AI and 3D modeling.
Right.
But as with any powerful tool, it's important to think about how this advancement might change the game and not just in the tech world.
It's true. We're talking about a technology that could revolutionize everything from like how we design buildings to how we experience entertainment.
Yeah.
But with that potential comes like a responsibility to really think about the broader impact.
Absolutely. One of the first things that comes to mind is how this might impact jobs,
Yeah.
especially for people who work in fields like 3D modeling and animation.
It's a valid concern. I mean, whenever we introduce automation, there's always that period of adjustment.
Yeah.
But rather than thinking of it as like AI replacing human creativity, I see it more as a collaboration.
So imagine AI handling those repetitive, time-consuming tasks that artists and designers often face, freeing them up to focus on the more creative and strategic aspects of their work.
Exactly. It's like giving every artist like a team of digital assistants that can work tirelessly on all those technical details, allowing them to explore new ideas and push their creativity even further.
I like that perspective. Instead of replacing jobs, it's augmenting human capabilities.
Right.
And what about the accessibility factor? We talked about how Phidias makes 3D modeling easier for anyone to use.
Right.
What kind of impact could that have?
Well, the democratization of these tools is incredibly exciting. Imagine a world where anyone with an internet connection and a bit of imagination can design their own video game characters, create custom 3D printed objects for their home, or even build virtual prototypes for inventions they've only dreamed of.
It's like taking the power of a Hollywood studio's special effects department and putting it in the hands of everyday people. The creative potential is staggering.
It really is. And it's not just limited to individuals.
Right.
Think about the possibilities for education, where students could interact with historical artifacts in virtual reality or explore the human body from the inside out using 3D models generated in real time.
Okay, you're really painting a picture of a future where learning is so much more engaging and immersive.
Exactly. And that's just scratching the surface. In healthcare, surgeons could use AI-generated 3D models to plan intricate surgeries with unprecedented precision. Architects could design entire cityscapes, testing out different materials and layouts, all within a virtual environment that responds to their input in real time.
Wow, those are some serious game changers.
Right.
But as we venture further into this uncharted territory, are there any potential downsides we should be mindful of?
Of course. One concern is ensuring that these powerful tools are used responsibly.
Oh, okay.
Think about the potential for creating incredibly realistic 3D models.
Okay, I'm starting to see where you're going with this.
Yeah.
If it's that realistic, what's stopping someone from using it to create misleading or harmful content?
Exactly. It's a valid concern, and it highlights the need for ongoing conversations about ethics and guidelines for the development and use of these technologies. Just like with any powerful tool, it's up to us to establish safeguards and ensure that it's used for good.
It's almost like we're stepping into a science fiction novel, but it's our reality now. We've got these incredible tools at our fingertips, and it's up to us to figure out how to use them wisely.
I agree. And that's why discussions like this are so important.
Yeah.
By talking about the potential benefits and challenges, we can work together to shape a future where AI-powered 3D modeling enriches our lives in positive and meaningful ways.
Couldn't have said it better myself. Okay, we've covered a lot of ground here, from the technical nitty-gritty to the mind-blowing potential impact of Phidias, but we're not done yet. And we're back for our final act of our Phidias deep dive. We've talked about how it works, the potential impact, but now I'm really curious about what the future holds for this technology, what's coming down the pipeline.
Yeah, it is exciting to think about. We've been looking at excerpts from this research paper, but this is really just the tip of the iceberg. The field of AI is evolving so rapidly, and the possibilities with 3D modeling are practically limitless.
Limitless is a good word for it, because we're not just talking about creating these static models anymore.
Right.
What really gets me fired up is the idea of these models coming to life, becoming interactive and dynamic. Is that something that researchers are working towards?
Absolutely.
Yeah.
One area that has huge potential is integrating this technology with virtual reality and augmented reality.
Okay.
Imagine not just seeing a 3D model on your screen,
Right.
but actually being able to walk through it, interact with it as if it were physically there.
Okay, now we're talking. That would revolutionize so many industries. Architects could give their clients these virtual tours of buildings before a single brick is even laid. Product designers could test out prototypes in these immersive environments, seeing how they look and function under different conditions.
Absolutely. And we can't forget about entertainment.
Right.
Video games could become even more immersive, even more realistic.
Right.
Imagine exploring these vast AI-generated worlds that feel truly alive with environments and characters that respond to your every move.
It'd be like stepping into your own personal sci-fi movie.
Right. It's incredible.
And you mentioned healthcare earlier.
Right.
What kind of advancements are we looking at on the horizon there?
I think one of the most exciting things is personalization.
Okay.
Imagine doctors using AI to generate these 3D models, but of your specific anatomy.
Wow.
To plan surgeries or therapies that are tailored to your unique needs.
Okay.
It could be a game changer for everything from treating sports injuries to developing new prosthetics that seamlessly integrate with the human body.
That level of personalized medicine would be incredible. It feels like we're on the verge of this whole new era in healthcare where technology is empowering us to live healthier, longer lives.
I agree.
But with all this talk about potential, it's easy to get caught up in the excitement of it all.
Right.
Are there any challenges or concerns that we should keep in mind as this technology continues to evolve?
Yeah. I mean, you're right. It's important to stay grounded.
Yeah.
I think one ongoing challenge is really ensuring that these advanced tools remain accessible to everyone.
Right.
We don't want to see a future where only large corporations or institutions have access to this kind of creative power.
Yeah.
It's crucial that we continue to democratize these tools,
So,
make them available to artists, to students, to anyone with the drive to create.
that's a great point. The beauty of Phidias and these similar AI models is that they have the potential to level the playing field,
Right.
giving individuals and small teams the ability to compete with those industry giants. We need to ensure that that remains a priority as this technology keeps advancing.
Absolutely.
Mm.
And as AI becomes more sophisticated,
Mm.
I think there are always going to be those important discussions about the ethical implications. We need to be mindful of potential biases in the data that's used to train these models.
Yeah.
And just ensure that any of that AI-generated content is used responsibly and ethically.
It's a reminder that as much as we love to explore all the possibilities of technology, we need to be having those conversations about ethics and responsibility along the way.
Absolutely.
We can't just focus on what can be done. We need to think about what should be done.
I couldn't agree more. Ultimately, I think the future of AI-powered 3D modeling really depends on collaboration
Yeah.
between researchers, developers, policymakers, and the public. It's about working together to shape a future where technology empowers us, inspires us, and benefits all of humanity.
That's a great note to end on. We've covered so much in this deep dive. From those technical innovations of Phidias to those far-reaching implications of AI-powered 3D modeling. And it's clear we're just scratching the surface of what's possible. And I, for one, am both excited and a bit awestruck by what the future holds. What about you?
Oh, I completely agree. It's an incredible time to be witnessing these advancements firsthand. Who knows what amazing creations we're going to see in the years to come. But one thing's for sure, it's going to be a wild ride.
And on that note, we'll wrap up this deep dive, but the conversation doesn't end here. We want to hear from you, our listeners. What are your thoughts on AI-powered 3D modeling? What excites you? What concerns you? Share all your thoughts with us on our social media channels, and let's keep this conversation going. Because the future of this technology is something we'll all be shaping together. Until next time, keep those imaginations running wild.
Ever get that feeling like you're trying to talk to a search engine in a language it just doesn't understand?
Totally. You spend all this time trying to guess the exact right combination of keywords.
Yeah, exactly. Like you're stuck in some kind of keyword guessing game. Well, for today's deep dive, we're ditching the rulebook and taking a look at the future of search.
A future where AI actually gets what you're looking for without jumping through all those hoops.
And to help us unpack all this, we're diving into a paper called Promptriever. Instruction-trained retrievers can be prompted like language models.
Oh, I'm so glad we're talking about this one. It really caught my eye. We're talking about a whole different way of looking at how we interact with information.
Right. So let's jump right in. This paper introduces something called Promptrievers.
Which is basically this super cool AI model that's been trained to respond to instructions you give it in plain English.
Okay, so instead of having to type in like James Cameron, movies, pre-2022, not co-directed, all those specific keywords.
You could literally be like, find me movies by James Cameron, but only those released before 2022 and not co-directed.
And it can actually handle all that.
That's the idea. It's designed to understand all that nuance.
That's amazing. So how does it get so good at understanding those little details? The paper mentioned something called instruction negatives, which sounds kind of intense, honestly.
Yeah, it's kind of like AI boot camp or something. Basically, imagine you are showing the AI a bunch of search results that are almost right, Things that might seem relevant at first glance, but they don't quite line up with the instructions you gave. Those are instruction negatives.
So say you're researching volcanoes, and you specifically want information on types of volcanoes that haven't erupted. But the AI might accidentally include a document about, I don't know, the environmental impact of volcanic eruptions.
Exactly. It's related to volcanoes for sure, but not what you're really getting at.
Right.
And these instruction negatives are how the AI learns to differentiate between those things, so it becomes super specific about what you actually want.
So it's kind of like training a bloodhound to sniff out exactly what you're looking for, but instead of a scent, it's all about understanding the nuances of language.
Yeah. And get this, the researchers actually found that you can use specific phrases to nudge prompt retrievers towards giving you even better results.
Really? Like, what do you mean? Like saying, think step by step, or let's break this down. Are you saying we can have motivational talks with our search engines now?
Well, Maybe not motivational talks exactly, but the paper did show that using prompts like think carefully when assigning relevance can actually make a difference.
Wow.
It seems like even subtle cues like that can really help Promptriever zero in on what you need.
So it's not even just about understanding what we're looking for, but it's also about how we ask, I guess.
Exactly.
This is really making me rethink how we might be interacting with AI down the road.
Oh, for sure. It's a whole new ballgame, right? We've always been trying to think like a computer to get what we want.
Right.
Now the tables are turning. The computer is learning to think like us.
And what does that mean, practically speaking? Paint me a picture here. What could a future powered by this kind of tech actually look like? So imagine this. You're working on some huge project, right? Maybe you're even putting together a podcast episode about some really complex AI research.
In there.
Totally. But instead of having to wade through tons of search results, you've got this AI assistant and it just pulls out the most important information. Boom.
And not only that, but imagine it can actually understand that information for you. Synthesize a whole research paper, highlight all the key takeaway, even point out things like potential biases or gaps in the data.
It's like having your own team of super smart research assistants on call 24/7.
Exactly.
So instead of getting lost in all the details, you could use AI to kind of get the big picture instantly.
Right.
And then you can really dive into the stuff that's most important for you. That would change everything. From how we learn to, pretty much any field you can think of where having the right info is key.
It is. And that's actually what makes this research so exciting to me. It's not just, a small step forward. It's a totally different way of thinking about how we interact with information in general.
Right.
A future where AI doesn't just find information, but helps us make sense of it, analyze it, use it to make smarter choices.
It's like going from riding a horse to piloting a spaceship. We're talking about a whole other level of understanding and efficiency.
Totally. And even though it's early stages, this kind of research gives us a glimpse of what that future might look like. A future where we've got all the information we could ever need right at our fingertips.
And it's all unlocked with AI. Well, this deep dive has definitely given us a lot to think about. If AI can get this good at understanding exactly what we're looking for in a search, what other super complex tasks could we teach it to do in the future? That's something to ponder, right?
Definitely.
As always, thanks for exploring with us today. And until next time, keep asking those big questions and keep on diving deep.
Ever scrolled past a video online and thought, wow, how they even make that? The special effects are so good, Well, get ready, because today we're diving into AI that can generate high-quality video from a single image.
It's mind-blowing stuff, really.
No kidding. We're talking one-click video creation. Forget those hours of rendering we're used to. This is the future, or at least getting closer to it.
It is. And that's the incredible potential of OSV one-step video generation, which is what this research paper we're looking at today is all about.
One-step video generation. That's got a ring to it, I gotta say. But before we get too far ahead of ourselves, maybe back up a bit. Why is this such a big deal? We already have AI that makes videos, right?
That's true. But think of it this way. Traditional video diffusion models, they're kind of like those friends, the ones who are always running late, no matter how much notice you give.
Oh, I know the type.
Right. That's these models. They're slow. They're seriously resource intensive. Picture needing a supercomputer just to whip up a 10-second clip for, your social media.
Okay, computationally expensive. Got it. But what makes it such a resource hog? It's just moving pictures, isn't it? How hard can it be?
Way more complex than it seems. Imagine you've got this perfectly clear image, right? And then you start slowly adding noise to it, like static graininess, until it's just this blurry mess. Now imagine trying to reverse that whole process, but it's not just one image, it's a whole bunch of them, all changing slightly to make a moving picture.
Oh, okay, so it's like unsolving a puzzle, but with a ton of pieces, and they all have to move together smoothly.
Exactly. And to do that, these models use some seriously heavy-duty math, something called a probability flow ODE. Basically an equation that helps figure out how all those tiny details in each frame fit together, but also how they change over time to create motion. And solving that equation over and over for every single frame, that's what eats up all the computing power.
So definitely not something I'm going to be doing on my old laptop then. No wonder people are trying to find a better way. The paper did mention some other solutions, though, like that animate LCM thing. What's that all about?
So animate LCM uses this really neat technique called consistency distillation. So it's like,
Yeah.
imagine training a mini version of a much larger AI.
Ah, like an apprentice learning from a master craftsman.
Exactly. So you try to distill all that knowledge and skill into a smaller, faster package.
Hmm.
And while Animate OCM shows a lot of promise, it kind of stumbles when you want to generate video in just a few steps, let alone one step.
Mm-hmm.
The quality tanks.
So close, but no cigar. Didn't some researchers try using GANs for this? Those generative adversarial networks we talked about before, weren't those supposed to be good at generating realistic stuff?
They are. And they have been used for video. Picture this. Two AI teams, right? They're in a video editing showdown, constantly trying to one-up each other with more realistic, more impressive footage.
Sounds intense. But if they're so good, why didn't they work out for this one-step video idea?
Well, GANs, they have a bit of a reputation. They can be kind of temperamental. Like training them is sometimes like building a house on a foundation that keeps shifting.
Yeah.
Not exactly ideal for that whole one-click dream, right?
Definitely not. There was also that whole latent space thing mentioned in the paper. What's that about?
Right, the latent space. Think of it this way. Imagine trying to cram this huge, intricate sculpture into a tiny little box. Not going to happen, right?
Right.
So you need to find a way to compress it, represent all the important details in a smaller, simpler form. That's basically what latent space does.
So like a blueprint of the video data instead of the whole bulky thing.
You got it. This compressed blueprint is way more efficient for the AI to work with, but all that compressing and decompressing, it adds another layer of complexity. And for our already moody Jans, it makes them even more prone to those meltdowns during training.
Okay, so we've got these existing solutions, but all with their own quirks. And speed, efficiency, that's the name of the game here. Which is where OSV waltzes in and says, hold my drink, apparently. What's so special about it?
It's like OSV took the best parts of all those other ideas, smoothed out the rough edges, and then added its own secret sauce. And trust me, it's a recipe for success.
Okay, you've got me hooked. Tell me more about the secret sauce. What makes OSV tick?
Well, they actually start with a two-stage training process, which is interesting in itself. In stage one, they DOUs Jans, but in a very strategic way. Remember our AI video editing rivals?
Oh, yeah, the showdown.
Right, so OSV is like, all right, guys, you're good at the initial brainstorming, go wild. They let the Jans loose to quickly generate like a rough draft of the video.
Makes sense. Use their speed to our advantage. So then stage 2 is where it gets refined.
Exactly. They combine the Jan with that consistency distillation we talked about, like bringing in a master craftsman to, polish that rough draft into a work of art.
I like the analogy. But how do they get around that whole latent space instability issue? Especially with the GAN still being in the mix.
That's where it gets really clever. Instead of decoding the entire video in that compressed latent space, they use a pre-trained image AI called Dino V2. But, and here's the kicker, they tweak it so it can understand the temporal information that changes over time without having to unpack everything.
So like they're teaching an art critic who already understands paintings how to analyze sculptures, but without having to see every single detail of the sculpture first.
Perfect analogy. It's incredibly efficient, reduces the computational burden significantly, and thus less instability. And that's not all. They also have this multi-step consistency model solver. It's like imagine your GPS, right? And it's constantly reevaluating the route, making tiny adjustments to make sure you're always on the fastest path.
Okay, so always optimizing, gotta be efficient. I like it.
One more trick. The time travel sampler, or TTS. It's a bit technical, but basically it lets OSV explore different possibilities during training. Like, think of those choose-your-own-adventure books where your decisions change the story.
Oh, I loved those as a kid.
Right. So TTS is like that. For the AI, it helps it discard paths that don't work and focus on the ones that lead to better results.
Okay, so they're really pulling out all the stops here. But the real question is, does it work? Give me the results.
They're impressive, I have to say. In their tests, OSV consistently outperformed existing methods, especially at those low step counts, like 1 or 2 steps.
Which is the goal, right? One step, high quality, boom. Did they compare OSV's one-step quality to what the other models could do with multiple steps?
That's the best part. OSV, with just 1 step, was producing video quality on par with those other models using multiple steps.
No way. That's like winning a marathon while everyone else is still tying their shoelaces.
So what does this mean for the average person? Am I going to be making Scorsese films from my phone now?
Well, maybe not Scorsese just yet, but it's definitely a huge step toward that kind of democratization of video creation. Imagine creating like professional-looking videos for your social media, website, whatever, all from your laptop with just a few clicks.
Okay, that I can get behind. It's like having your own personal editing studio, but without needing all the fancy gear.
Exactly. And it goes way beyond personal use, too. Think education, journalism, even healthcare. Teachers could make engaging video lessons in minutes. Journalists could have high-quality video reports from the field instantly. The possibilities are endless, really. It's mind-blowing when you think about it, kind of like when we all switched from those clunky camcorders to just recording videos on our phones. Suddenly, everyone's a potential filmmaker. OSV has that same vibe, that potential to completely change how we create and consume video.
It's a very exciting time to be a creator, that's for sure. But even with all this progress, it's still early days, you know. There are always limitations, challenges to consider.
Right. Can't all be sunshine and cinematic rainbows. What are some of those limitations they found?
Well, one thing they pointed out is that while OSV is amazing at generating video from a single image, it's still very reliant on that image for motion cues.
So I couldn't just give it a picture of my cat and expect it to, like, generate a video of her doing backflips.
Not yet, at least. The technology is not quite there yet. But knowing how fast this field moves, who knows? Maybe someday we will have those backflipping cat videos.
So maybe no backflipping cats right this second, but still, it's easy to get excited about the potential here. It's like we're on the edge of, like, a whole new creative boom, and OSV is that first spark.
I think so, yeah. Imagine a world where anyone, even if they have zero technical skills, can bring their video ideas to life in just a few clicks. It's almost like those barriers between, you know, having an idea and actually creating something. They're just dissolving.
It really is incredible. Like, what would this mean for how we tell stories, do you think?
Oh, man, that's a big question, but an exciting one. We're talking about a fundamental shift, right? Imagine video games that generate scenes in real time based on the choices you make as a player. Or how about personalized educational videos that adapt to how you learn best? We could even have these immersive virtual tours of historical events, almost like stepping back in time.
Whoa, okay, now that is pretty wild to think about. And it's not just about making new stuff either. What about bringing oldie media back to life? Could you use this to, like, remaster old films, maybe even generate whole new scenes for them?
No, that's a fascinating thought. I love it. Imagine, like, watching those classic silent films, but with realistic sound and color that the AI generated. Or documentaries where you could have historical figures, you know, speaking directly to you. The line between what's real and what's created, it could become really, really interesting.
It really feels like we're on the cusp of this whole new era of visual storytelling, where the only limit really is our imagination. But I guess as with any new tool, especially a powerful one like this, we have to at least consider the downsides, right? Is there a chance this technology could be misused?
It's the other side of the coin, isn't it?
Right.
Any powerful tool has that potential for misuse. Absolutely. I think the key is to be aware of the risks and to have these open, honest conversations about the ethical implications as this technology keeps developing.
So how do we navigate this new frontier responsibly then? What can we actually do to make sure this technology is used for good?
It starts with awareness, education, like we're doing now. The more people who understand the hows and whys, the potential benefits, AD, the risks of this tech, the better equipped we are to use it ethically and to, you know, really advocate for the right safeguards.
And that's not just on the shoulders of the people creating this technology either, is it?
Definitely not. It's all of us. We're all stakeholders in this.
Yeah.
Having those thoughtful conversations, demanding transparency from the companies developing these tools, being discerning about the content we consume online, it all matters.
It's a lot, for sure. But ultimately, it feels hopeful, right? Like, the future of this technology really is in our hands, and who knows? Maybe someday soon, those backflipping cat videos won't be so far-fetched. For now, though, that's our deep dive into one-step video generation and OSV. It's a wild world out there, folks, and it's only getting wilder. Thanks for exploring it with us.
Ever feel like we're all kind of just winging it?
What do you mean?
You know, like as a society, making decisions, setting policies.
Yeah, okay. I see where you're going with this.
Is there some secret formula for understanding how it all works? Or are we just stumbling through the dark?
Well, what if I told you researchers are getting really close to finding that formula?
You're going to have to elaborate on that one.
And they're using AI to do it, simulating human behavior on a massive scale to see what makes us tick.
Okay, now we're talking my language. We're diving into some seriously cool research today, folks. We're talking AI, but not like write me a poem AI. This is next level stuff.
Exactly. This isn't about AI writing your emails. This is about using AI to simulate human behavior on a massive scale. Think millions of simulated people, each making decisions, interacting, creating the surprisingly accurate model of, well, us.
This is Agent Torch, right? I skimmed the research paper, and honestly, some of it went straight over my head, I'm not going to lie.
It's dense stuff, for sure, but that's why we're here to break it down. So Agent Torch, it's a new framework, and it uses something called large language models, LLMs. You've heard of those, right?
LLMs. Okay, yeah, those are like the brains behind ChatGPT and all those predictive text things, right? Like when your phone tries to guess the next word you're going to type.
Exactly. But instead of finishing your sentences, Agent Torch uses LLMs to power these individual agents within a simulation.
Agents, huh? Like secret agents. This just got interesting.
Opposite. Not quite James Bond, but you're on the right track. Think of them as digital representations of real people. Each agent gets fed all this information, age, job, maybe even how worried they are about, say, a new virus. And then they use that information to make decisions, just like we do in the real world.
So instead of saying, okay, 20% of people will get vaccinated, this model can factor in all those individual things that make us tick, like how old someone is, what their job is, all those external factors.
Precisely. The researchers wanted to see if they can make these simulations really, really realistic. So they used data from New York City during the COVID-19 pandemic. Talk about a real-world test case, right?
Hold on. Did they simulate the entire pandemic in NYC? Like with millions of tiny AI New Yorkers running around making choices?
They did. And get this, the results are fascinating. They fed the AI all this information. Demographics, infection rates, even how long the pandemic had been dragging on. And they found that they could predict things like employment rates with incredible accuracy.
You're saying they could tell how many people would show up for work based on how burnt out they were on, like, Zoom calls and sourdough bread?
Chuckles. It's more nuanced than that, but essentially yes. Factoring in those human elements, like pandemic fatigue, it made the predictions way more realistic.
Wow. But there's got to be a limit to how much detail you can put into this, right? I mean, we're talking about millions of people here, even if they are AI. Doesn't that require an insane amount of computing power?
That's the really clever part. The researchers realized they didn't need to simulate every single person in excruciating detail. Instead, they came up with this concept of archetypes.
Archetypes. Okay, so is that like the jock, the nerd, the class clown? But, you know, for AI people.
You could say that. Imagine grouping those millions of agents based on characteristics and behaviors that make them act in similar ways. So instead of asking 8 million separate AI people what they do, they figured out a way to ask one representative from each group.
So instead of 8 million separate AI thought processes, it's more like a couple hundred. That's brilliant. But how do they know those groupings will give accurate results?
That, my friend, is the million-dollar question, and it gets to the heart of why this research is such a big deal. But I think we should save that for our next segment.
All right, so last we left off with these archetypes. They sound like a pretty clever way to get around that whole computing power problem. But how do they actually work in practice?
It's all about finding that balance between having enough detail and making the simulation actually run.
So it's a trade-off.
Exactly. It's like if you were trying to predict the weather and you tried to analyze every single air molecule on the planet.
That sounds like a nightmare for your computer.
And completely unnecessary. Instead, what do meteorologists do? They look for patterns, right? They group similar areas together based on things like temperature or pressure.
So instead of tracking every single raindrop, they're saying this whole area is acting like a rain cloud.
Precisely. It's the same idea with Agent Torch. The researchers had to figure out what are those key characteristics for people? What makes them behave similarly in different situations?
So what do? Just pick a few things at random?
Oh, no, they got really granular here. They fed the LLMs mountains of real-world data from New York City. Stuff like demographics, income levels, even commute times on public transport.
I'm guessing they had to teach the AI what a subway was first.
Laughing. You know, I never actually thought about it like that, but yeah, probably. The point is they wanted to capture as much of that real-world complexity as possible.
Okay, so they have all this data. They've grouped their agents into these archetypes. But how do they know if it actually works?
Well, they tested it. That's the beauty of simulations like this. You can actually compare them to what happened in the real world.
So they ran the Agent Torch simulation and how'd it do?
It did surprisingly well. They looked at things like those employment rates we talked about, which were hugely affected by the pandemic. And even with the archetype approach, Agent Torch was able to make some pretty accurate predictions.
That's wild. So just by grouping similar agents together and asking one representative from each group what they do, they're still able to get a good sense of how the whole system behaves.
That's the power of this approach. But it begs the question, why go through all this trouble in the first place? What's the point of building these super detailed simulations?
Yeah, good question. I mean, it's cool and all, but is it actually useful for anything beyond just recreating the past?
That's the really exciting part. We're not just talking about looking back, we're talking about looking forward. Using this kind of simulation to make better decisions in the future.
So it's like a time machine for policy decisions.
Exactly. We can start to run all these what-if scenarios, like, what if we tried this policy or that intervention? How would people react?
And that's something we just haven't been able to do before.
Not on this scale, no.
Yeah.
Imagine being able to test out different public health measures, economic policies, even urban planning strategies, all in a safe virtual world before you try to implement them in the real one.
Okay, when you put it like that, it does sound incredibly powerful, but
Yeah.
you know what they say? With great power.
Comes great responsibility, I know. And this technology is not without its challenges. There are definitely ethical questions that come up.
And potential downsides.
Absolutely. No technology is perfect, and we need to be incredibly thoughtful about how we use something like this, but that's a whole other conversation.
So we've talked about the power of Agent Torch, the potential it has. But we've got to talk about the elephant in the room, right?
I'm with you. For all the good it can do, there are some pretty big what-ifs here.
We're talking about simulating human behavior down to what feels like a science. Doesn't that kind of freak you out a little?
It's definitely a lot to unpack.
If we can use AI to get this good at predicting how people will act, what does that even mean for, like, free will? Are we all just robots following some invisible code?
That's a question philosophers have been debating since, well, forever. And I don't think Agent Torch has the definitive answer.
Like, we still have to figure out what it even means to be human.
Exactly. But it does give us this amazing new tool to explore those questions, to understand the how and the why of human behavior.
Okay, but let's say these simulations get even more accurate, even better at predicting what we'll do. Isn't there a point where it gets, I don't know, dangerous?
I see what you're saying. Any technology can be misused, right? And a tool this powerful, well, it could definitely be used for bad as much as for good.
It feels like there are some ethical lines in here somewhere, you know? Like, if you can predict how people will react with that level of certainty, what's stopping someone from exploiting that?
You're right to be thinking about that. And that's why it's so important to have these discussions now while this technology is still developing.
So we can set up some guardrails before it's too late.
Exactly. This isn't just about what we can do, it's about what we should do. And that should involves a lot of different voices. Scientists, ethicists, policymakers, even the general public.
So it's a team effort to make sure this kind of AI gets used responsibly.
100%. This technology has the potential to reshape so much of how we understand the world, how we make decisions. We have to be mindful of that.
On that note of cautious optimism, I think we're about at the end of our deep dive.
Time flies when you're talking about the future.
It really does.
Yeah.
But before we go, I have to ask, what's next for this whole Agent Torch thing?
It's still early stages, but the possibilities are, frankly, kind of mind-blowing. Imagine incorporating social networks, cultural influences, even individual psychology into these models.
So we're not just simulating what people do, but how they think.
It's all on the table. And the potential benefits for things like public health, economics, heck, even urban planning, they're huge.
It's a lot to wrap our heads around. But I think that's a good place to leave it for today. Big thanks to you for breaking this all down for us and to you, our listeners.
Always a pleasure.
Until next time, keep those brains buzzing. And remember, the future is full of possibilities. It's up to us to shape it responsibly. All right, we're diving into quantized LLMs today. I know you hear about these big, powerful AI models all the time, but have you ever thought about how to make them smaller, more efficient?
It's pretty amazing we can shrink these models down. And a lot of the time, they perform just as well as the original.
So it's like we're taking a whole library and we're condensing it down into something you could hold in your pocket.
Exactly. All the information is still there, just packaged in a much smaller, more efficient way.
That's quantized LLMs in a nutshell. And we're taking a deep dive into a paper all about it. It's called A Comprehensive Evaluation of Quantized Instruction-Tuned Large Language Models, an experimental analysis up to 405B.
They really tried to be comprehensive, too. They looked at models ranging from 7 billion parameters to 405 billion.
Wow.
Yeah, it's a huge range.
So we're talking about comparing like a bicycle to a jumbo jet in terms of complexity.
A very appropriate analogy.
And they didn't just compare sizes either.
Yeah.
They ran these models through a battery of tests.
13 different tests, in fact.
13.
13. Each one designed to test different capabilities.
So it's like we're trying to get a full picture of each model's personality.
I like that analogy.
And to do that, you can't just rely on one conversation, or in this case, one test.
You've got to get to know them a little better.
Exactly. And that's what makes this research so interesting. It's not just about shrinking these models. It's about understanding how different methods of quantization
Right. Because there are several ways to quantize a model.
impact their performance.
It's like choosing the right spice level for your food.
I like that.
Some people like it mild, some like it hot. It all depends on what you're going for.
So how do we find that perfect balance between shrinking a model and maintaining its performance? What were some of the surprises, even for the researchers?
Well, one of the most interesting things they found was sometimes these smaller models actually perform better than the original larger models.
Hold on. You're telling me shrinking these models doesn't always mean sacrificing performance.
Not always. Sometimes it actually makes them better.
That's incredible.
Yeah.
Almost hard to believe.
I know, it's amazing. It really challenges our assumptions about AI.
It really does. So it's not just about making these models smaller. It's about understanding how those changes actually impact what the model can do.
Exactly.
And how do we find that sweet spot?
That's the million-dollar question.
That's what we're trying to figure out. And this research gives us some really important clues. But before we jump into those, I want to know, what are some of the details from this paper that really stood out to you?
Well, they dove deep into different quantization methods. And one of the things that I found really interesting was how some of these methods, they worked great on smaller models, but when you tried to use them on a massive 405 billion parameter model, they struggled.
Really?
Yeah, it's like they couldn't handle the sheer scale of it.
So it's like trying to fit a square peg in a round hole.
Kind of. You need the right method for the right size model.
It's all about finding the right tool for the job.
Exactly.
This is already so fascinating, and we're just getting started. We'll be back right after this quick break to dive even deeper into this groundbreaking research. Stay with us. All right, so we're back, and we're really starting to uncover some fascinating insights here.
We are. It's amazing to see how these quantized models are performing.
Right, like you were saying before the break, sometimes they even outperform the larger models.
Exactly. And it's not just a one-off thing either. The researchers found several instances where the smaller models were actually better.
Do you have a specific example, something from the paper that really jumped out at you?
Well, there was this one task. It was from the GSM-8K benchmark, which is all about elementary level math problems. And in some cases, the quantized model actually did better than its larger non-quantized counterpart.
Wait, you're telling me a smaller model did better at math than a bigger one? That's wild. How is that even possible?
It is pretty counterintuitive, isn't it? But that's the beauty of research like this. It challenges our preconceived notions. In this case, it seems like the quantization process might actually introduce some efficiencies.
So it's like by forcing the model to work with less, it actually becomes better at certain things.
Exactly. It's like that old saying, constraints breed creativity.
I love that. It makes you wonder if sometimes we're overthinking things.
It really does. Maybe simpler is better sometimes.
Maybe so. But this also makes me wonder about the practical implications of all of this.
Right, because this isn't just theoretical. This has real-world applications.
Exactly. So what does this mean for people like you and me? People who might want to use these models in our everyday lives.
Well, for one, it means we might not need massive supercomputers to run these powerful AI models.
Okay, so we're talking about making AI more accessible.
Exactly. More accessible and more affordable.
That's huge.
Yeah.
It's like leveling the playing field.
I like how you put that, because for a long time it's felt like AI was this exclusive club. Only the big tech companies with tons of resources could really play.
Right. But now it seems like things are changing.
They are, and that's incredibly exciting.
I'm with you on that one.
Yeah.
This research is really giving us a lot to be optimistic about. But like with any new technology, I'm sure there are potential downsides we should be thinking about too.
Absolutely. And that's something we can't shy away from.
So what are some of the potential pitfalls of making AI more accessible?
Well, like any powerful tool, there's always the risk of misuse. And the more widespread a technology becomes, the more important it is to use it responsibly.
That makes sense. So how do we ensure that these quantized models are used for good and not for something harmful?
That's the million-dollar question, isn't it? And there's no easy answer. But I think the first step is starting a conversation. We need researchers, developers, policymakers, everyone really to come together and talk about these issues.
So it's a collaborative effort.
It has to be. We all have a stake in this.
I completely agree, and I think this research does a great job of getting that conversation started. It highlights both the incredible potential of quantized LLMs and the importance of approaching this technology thoughtfully and responsibly.
It's a delicate balance, but it's a balance we need to find.
Couldn't have said it better myself.
Yeah.
So what's next? Where do we go from here?
Well, I think the next step is to really dig into these different quantization methods, to understand their strengths, their weaknesses, and how they can be applied to different types of models and tasks.
So there's still a lot more to learn.
Oh, absolutely. We're just scratching the surface here.
This is so exciting. I feel like we're on the verge of a major breakthrough in AI.
I agree. And who knows what incredible advancements await us.
This is definitely a deep dive I won't soon forget. But we've got to take another quick break. Don't worry, though. We'll be back in a moment to wrap things up. Stay tuned. And we're back. I feel like we need to take a second just to process everything we've talked about. It's a lot to take in.
It really is. Quantized LLMs are changing the game.
You know, it reminds me of when we first started compressing digital music.
Oh, yeah.
We went from these big clunky CDs to MP3s that could hold like 100 times more songs.
And now we've got streaming services with millions of songs.
Exactly. And it seems like we're on that same trajectory with AI.
Totally. We're making it smaller, more efficient, more accessible.
But like with any new technology, there are always those bigger questions. Like, how do we make sure this technology is used for good?
That's the million-dollar question, isn't it?
It really is.
And I think it's something we need to be thinking about from the very beginning.
So they need to be proactive, not reactive.
Exactly. We can't just wait for problems to arise. We need to anticipate them and come up with solutions.
So it's not just about building the technology, it's about building it responsibly.
100%. And that's going to require a collaborative effort.
Right. We need researchers, developers, policymakers, even everyday users to be part of this conversation.
Everyone has a role to play.
I completely agree.
Because at the end of the day, we all want the same thing. We want to use this technology to make the world a better place.
Absolutely. And I think this research shows us that we're on the right track.
Yeah.
We're finding smarter, more efficient ways to leverage the power of AI.
And we're making it accessible to more people.
Which is incredibly exciting.
Yeah.
So where do we go from here? What's next for quantized LLMs?
Well, I think we're just getting started. There's still so much to explore and so much potential to unlock.
This is definitely a deep dive I won't soon forget. It's clear that the future of AI is full of possibilities.
It certainly is.
Well, that's all the time we have for today's deep dive, but don't worry, we'll be back next time with another fascinating topic from the world of AI. Until then, keep exploring, keep asking questions, and never stop learning. Because the future of AI is being written right now, and it's up to all of us to shape it.
Ever wished you could just describe a sound and have it, magically appear?
Yeah, just think it and boom, there it is.
Exactly. Well, get ready because today's deep dive is going to blow your mind.
We're talking about AI that can compose original audio. And I mean everything, sound effects, music, you name it, from just, text prompts.
It's like having, I don't know, an AI Mozart or something. But instead of sheet music, it's using code.
And the really cool part is how this new model as audio is tackling the big problems that have always plagued this kind of tech.
Yeah, this research paper we're looking at really digs into the nitty-gritty.
Right, so older models, they usually relied on these things called spectrograms. They're kind of like musical fingerprints.
Musical fingerprints.
Yeah, they break down the sound into all these different frequencies, but they're really complex. And working with them, computationally speaking, it's a nightmare.
I bet. That sounds incredibly complicated.
It's like trying to paint a picture, but instead of using brushes, you're manipulating each pixel individually.
Oh, man. Talk about a headache.
Exactly. So as audio just bypasses all that, instead of spectrograms, it works with, get this, the raw sound wave itself.
Wow. So it's like speaking the fundamental language of sound.
Yeah, exactly. And by using this thing called a waveform VAE, short for variational autoencoder, it streamlines the entire process of generating that sound.
Okay, now you're just using big words to sound smart. But seriously, how does it actually work?
Okay, so imagine you're writing, right? But instead of having to think of each letter, you just think the thought and boom, the words appear on the page.
Okay, that's pretty cool. I could get used to that. But what really gets me is how this thing actually learns. It's like teaching a computer to understand sound.
It is, and the training process is fascinating. Think of it like a 3-course meal, right? First, you have the appetizer. As audio gets fed this massive data set of sounds called audio set.
Okay, so it's like loading up on all these different sounds. But then what? How does it actually make sense of it all?
That's where the main course comes in. As audio uses these things called captions, millions of them. It's like labeling each sound with a little text description. So like a dog barking or a car engine starting.
Ah, so it's connecting the sound to the words we use to describe it.
Exactly. But these captions, they're not just slapped on randomly. They're carefully created using some really sophisticated AI models, and then they're filtered for quality. Only the best for as audio.
So it's getting a gourmet meal of sound and text pairings. This AI eats better than I do. But hold on, there's a third stage, right? Like a dessert tray.
Spot on. After the massive data sets, as audio gets a final polish from a smaller, human-labeled set called audio caps.
So it's like sending it to finishing school.
Yeah, exactly. It's learning all the subtleties to create really high-fidelity audio.
Incredible. And to think, this is just the beginning. This is all super cool, but it makes me wonder about something.
Shoot.
We've talked about these huge data sets and all these crazy processes, but like, isn't audio data just, I don't know, really difficult to work with in the first place?
Yeah, for sure.
It's not like a picture where you can just, look at each pixel separately.
Absolutely. One of the big things with audio data is that it's time-based, right? So the order of everything is super important.
Makes sense.
Like imagine reading a sentence where all the words are just totally scrambled. It would be gibberish.
Totally.
And audio is kind of like, it's this continuous stream of sound. So how do you actually make sense of it?
That's a good question. How do you make sense of it?
Well, the architecture of as audio is really key, specifically this thing called a diffusion transformer. It's how it processes all that information.
Okay, break that down for me a little. What's a diffusion transformer?
So think of it this way. Imagine you're building a giant Lego set, right? But instead of having instructions, you just have this massive pile of bricks.
Oh man, my worst nightmare.
Right. It'd be total chaos. But what if you had these little notes scattered throughout and they were like, hey, this brick goes with that, one way over there.
Okay, I think I see where you're going with this.
Those notes, those are like Audio's long skip connections. They help it keep track of the relationships between different parts of the sound, even when there's just a ton of information coming at it all at once.
So it's like giving the AI a map to navigate this sea of sound data.
Exactly. And to make it even better, the researchers have optimized the architecture with all these other fancy techniques they call Edel, N-Soleil, and QK norm.
Kitschy.
Yeah, less. But the point is, these techniques help make the training process way faster and less memory intensive, which is super important when you're dealing with, mountains of audio data.
It's like they gave this AI the ultimate brain boost for processing sound. Okay, so let's talk about control. How do we actually, tell it what to do? How do we go from cat meowing to actual meows?
So here's where things get really interesting. As audio uses this thing called classifier-free guidance. CFG for short.
CFG, got it.
Think of it like, I don't know, a dial that controls how closely as audio sticks to your text prompt.
Okay, so like a volume knob for catness.
Sort of. Basically, the higher the CFG, the more literally as audio will interpret your prompt. But, and this is important, the researchers found that while higher CFG meant as audio was better at following instructions, the quality of the audio itself actually started to go down.
Interesting. So it's a trade-off. Yeah, it can perfectly mimic a cat meowing, but it might sound like it's coming through a tin can.
Yeah, exactly. And finding that sweet spot between following instructions and preserving quality is a big thing in this field.
So how'd they solve it? Is there a magic CFG number they figured out?
Well, instead of finding one magic number, they actually developed this whole new technique called CFG rescaling.
Okay, now you're losing me again. Laugh.
Fair enough. Basically, instead of just cranking up the CFG dial, they basically fine-tuned how as audio interpreted those instructions in the first place. They made it more nuanced.
So they taught it to follow directions without being like a robotic cat meowing machine.
Exactly. And the result, really realistic, high-quality audio, even from those, more abstract or complex prompts.
Amazing. Now, this paper goes on to compare as audio to some of the other big names in AI audio, things like Tango, Audio LDM, and Macon Audio. How does it stack up?
It's interesting, actually. Across the board, as audio seems to hold its own really well, and in many cases, it does even better. There's this one metric called freshet distance.
Freshet distance.
Yeah, it's basically a way to measure how similar the generated audio is to, real-world sounds.
Okay, that makes sense.
And when they compared as audio on this, it consistently scored better than the others.
So it's not just our ears thinking as audio sounds good, the numbers back it up too.
Right. And honestly, what's maybe even more impressive is how well As Audio did in the subjective tests.
You mean where they get actual humans to listen and judge?
Exactly. Apparently, they had these audio experts listen to samples, some made by As Audio, some made by these other models, and even some real-world recordings.
Ah, that's putting it to the test.
Yeah. And guess what? They consistently rated As Audio higher.
No way. Higher than the real recordings.
Well, not higher than the real ones, no. But they said it had a better overall audio quality and that it captured the text prompts better than any of the other models.
Wow. That's really something. So we're not just talking about an AI that's technically good. We're talking about something that's actually like creatively interesting too.
Right. It's like the difference between someone who can just play the notes on a page and a musician who can actually make you feel something.
Exactly. And that's what makes this all so exciting. It really feels like As Audio is pushing the limits of what we thought AI could do with audio.
Totally. It's like opening up a whole world of new sonic possibilities.
You know, it's funny. This whole thing has got me thinking about like the nature of sound itself.
Ah, how so?
Well, we usually think of sound as this like fleeting thing, right? Here 1 second, gone the next. But As Audio is creating it from scratch. It's like we're seeing, I don't know, the blueprint of sound or something.
It's an interesting way to look at it. Like we're uncovering this hidden structure beneath it all.
Right. Like, what are the fundamental elements that make, say, a bird song different from a crowd cheering? And now, with As Audio, it's all boiled down to code.
Exactly. And if we can actually understand those building blocks, imagine the possibilities.
Okay, I'm imagining. This is where it gets really exciting.
Think about composing music that evokes a specific emotion, or creating these soundscapes that have actual, like, therapeutic benefits, all tailored to the individual.
It's like a whole new world of sonic possibilities. And we're just scratching the surface.
Totally. I mean, imagine personalized soundscapes that change based on your mood. Or what about AI-generated film scores that are just as good as anything a human could compose?
Lost on man on a roll. What about devices that can communicate emotions through sound?
There you go. See? The potential applications here are just mind-blowing.
It really gets you thinking about the future of, well, everything audio, doesn't it? This deep dive into As Audio has really opened my ears to what might be possible.
Mine too. It's a testament to just how powerful AI is becoming. And of course, huge credit to the researchers pushing these boundaries.
Absolutely. Well said. And on that note, I think it's time to wrap up this deep dive.
It's been a blast.
To everyone listening, thanks for joining us as always. Until next time.
Keep exploring.
All right, what if you could, like, bottle up your best memories, like in 3D?
Oh, wow.
We're talking reliving that game-winning shot or, I don't know, your dog's best Frisbee catch. All those moments you wish you could just jump back into, but like in full, awesome 3D.
Yeah, it'd be like stepping right back into that memory. And what's cool is it's capturing reality, not just, designing something from scratch.
Exactly. But there's always been this catch, right? You practically needed a whole film crew following you around to get that much realism.
Way too many cameras for me.
Yeah, way too much processing power for most people.
That's always been the thing, right? The tech is so hungry for data. More cameras means more info, and usually that means a better 3D image at the end of it all. But who has the time for all that?
Not me. But that's what's so cool about this paper. Splat fields. Neural Gaussian splats for sparse 3D and 4D reconstruction might just be the answer. We're talking high-quality 3D, but with way less data.
Fewer cameras.
Faster processing.
The whole package.
This is amazing.
And that's what's so exciting. It's not even about adding more. It's about working smarter with what we've got.
Yeah.
Splatfields takes this really clever approach using something called 3D Gaussian splatting.
3D Gaussian splatting. Okay, that sounds kind of intense. Give us the breakdown.
Think of it like those splatter paint art projects.
Yeah.
But instead of paint on a canvas, we're talking virtual splats scattered in 3D space. And each splat has properties. Shape, color, how transparent it is.
So I'm picturing like this cloud of virtual paint splats, right? How do we go from that to like a whole scene?
Sure. That's where it gets really cool. Imagine looking at all these splats from all different angles, right? When you combine enough viewpoints, you build up the 3D scene.
So stitching together all these different perspectives, kind of like how our eyes work.
Exactly.
But you said this was just the starting point. What's the problem with regular 3D Gaussian splatting?
Well, it's like this. Imagine each of those splats is like a little independent artist, right? They're great at what they do, but they don't know how to play nice with others.
So like little divas, each doing their own thing.
Exactly. And when you've only got limited images.
Your cameras.
Yeah, fewer camera angles. these independent splats don't have the info they need to make a good picture. They just end up overfitting to the views they were trained on, which means as soon as you show them something new,
Disaster.
they just fall apart.
Total chaos. Like trying to paint a mural with a bunch of artists who won't even share their brushes.
Right.
And that's where Splatfield swoops in to save the day.
Right. Exactly. It's like Splatfields teaches these divas how to work together.
Okay. Yeah.
It introduces this idea of spatial autocorrelation, which basically means it makes splats that are near each other more likely to have, similar features.
So instead of just random paint splatters, it's like we've got a real artist in there making sure every splat has its place.
Right. It brings order to all that chaos and makes a much better picture in the end.
Love it. But spatial autocorrelation, even I have to admit, that's a mouthful. How does it actually work? We're not talking about real paintbrushes and palettes here, right?
That's where the neural networks come in. Splatfields combines these neural networks with something called a triplane representation to make all these splats work together.
Triplane representation, neural networks. Okay, got to stop you right there. Break this down for me.
Okay, so imagine you take our 3D scene and project it onto, say, 3 walls, right?
Right.
Like one for the front view, one for the side, and one for the top.
Okay,
That's our triplane representation. It's like a blueprint for the scene.
gotcha. 3 projections, 3 different angles on the same thing. What happens next?
So the neural networks step in and they look at this whole blueprint and they use that information to tell each individual splat what it should look like, its color, how see-through it should be, everything.
So instead of each splat just doing whatever it wants, it's got this neural network as its guide.
Exactly. And because the networks are looking at the whole scene, they can make everything match up, even if we only started with a few camera angles.
It's like those splats finally understand what they're supposed to be doing, right?
Yeah, you're part of a team.
Teamwork.
Yeah.
Okay, let's talk about the real world for a sec. Does Splatfields actually work? Or is it just a cool idea?
Well, the researchers actually tested it out. They used these data sets from Blender, which is this 3D modeling software. And
So it can make really realistic images.
yeah, it's known for it. And they also use something called the DTU dataset.
Which is,
It's famous for having these really hard real-world captures.
so they tested it with the computer-generated stuff and real-life scenes.
Yeah, and here's the thing. Splatfields was better at reconstructing scenes from limited viewpoints, like across the board.
Fewer cameras, better images, music to my ears.
Right, fewer cameras, faster processing, but the quality is just as good or even better.
Less is more. I love it. Any numbers we could throw around, give the listener something to be impressed by.
Well, they use this thing called Moran's eye. It basically measures how well all those splats are playing together.
So the higher the score, the better the image.
Exactly. And Splatfields, it scored higher in almost every test.
Amazing. Okay, so we've got solid 3D scenes. But what about movement? Can it handle that? We're talking about the 4th dimension here, time.
Things are about to get even cooler. Remember those neural networks we were talking about?
Yeah.
They can actually factor in time.
So we can actually reconstruct stuff like a basketball game or like a dance performance in 3D.
You got it. Splatfields uses these things called flow fields to basically tell those splats how to move over time.
It's like giving our paint an upgrade. Now it's like animated paint.
Yeah, something like that.
Okay, but that sounds super hard to pull off.
It definitely adds some challenges. The researchers actually used this data set called the OWLI data set, which is known for having like really realistic motion capture data stuff like dancers.
Really complex movement.
Very complex.
So how did it do? Was it able to keep up with the dancers?
It showed a lot of promise, but I'll be honest, there's definitely room for improvement, especially compared to some other top methods, like these things called NeurIFs.
NeurIFs.
Yeah, those are a whole other can of worms. We could do a whole other deep dive on those. For now, all you need to know is that they're really good at this kind of reconstruction. Splatfields isn't the absolute best at this yet.
But it's getting there.
It's getting there, which is super exciting to see.
It is. Okay, so we've got this tech that can capture both still and moving 3D scenes.
With way less data than before.
Lightning fast processing.
Right.
The possibilities are huge. I mean, it really feels like something huge is on the horizon. Remember how we were talking about bottling up memories in 3D?
Yeah.
With Splatfields, it's like not even science fiction anymore.
I know, right? It's getting real.
Imagine like reliving your favorite concert.
Oh, from right there in the crowd?
Exactly.
Yeah.
Or sharing that like championship winning goal, but you can see it from any angle.
And all that just from a couple of pics or videos.
The mind blowing. And it's not even just about
Yeah.
memories, right? I was thinking about like medicine. surgeons could use it to make these crazy detailed 3D models.
Totally. That would be huge for planning surgeries and stuff.
Game changer. And I bet architects would be all over this.
Oh, 100%. Imagine being able to, like, scan a whole building to see if anything's wrong with it.
Right. Or even just to visualize what those renovations would actually look like.
It's incredible.
But honestly, what gets me most excited is how accessible it could be. This isn't just some tech for people with fancy cameras and computers.
Exactly. Anyone could capture their world in 3D.
I love it. Think about the stories we could tell.
Oh, I know. Or even just, like, connecting with people in this whole new way. It's amazing.
It really is. It has the potential to, like, change everything. And that brings us to you, listeners. What would you capture if you had this power? What moments would you bring to life in 3D? Think about it, and we'll catch you on the next deep dive. Ever tried to zoom in on a photo only to find, like, your friend's face is just a blurry mess of pixels?
Yeah.
Or maybe you've seen those AI art generators.
Oh, yeah.
You know, the ones that can make a really cool scene, but then you look closer, and the details are, like, totally off.
Right.
It's kind of like the AI world is stuck in, like, an impressionist painting or something.
Yeah, I see what you mean. All about the overall impression, but not so much the finer points. And it's a good analogy, actually, because it gets at something that's really tough for AI image representation. Getting a computer to, actually see an image the way we do with all the, like, nuances and details, it's incredibly difficult.
So it's not as simple as, like, just showing the AI a bunch of pixels and hoping it figures it out.
No, not at all. I mean, think about it. Like, you don't just see an image as a grid of colored squares, right? You see shapes, you see textures, you see how it all kind of fits together. And that's what image representation is all about. It's about finding a way to encode all that visual information so the AI can actually, like, make sense of it,
Okay, so that's what we're diving into today. You sent over some research about this new technique, SL2A INR. And from what I understand, it's trying to, like, completely change the game for AI image representation.
Yeah, exactly. But before we get into all the specifics of SL2A INR, I think it's helpful to take a step back and talk about INRs in general. Implicit neural representations. So imagine you're, like, teaching an AI to paint. But instead of filling in individual pixels, you're teaching it to understand, like, the continuous flow of color and light across the canvas.
Interesting.
That's essentially what an INR does.
So it's less about, like, those individual pixels and more about, like, the image as a whole, kind of like how a painter sees a scene.
Precisely. Yeah. Now, the thing is, current INRs, they're promising, but they often fall into this trap called spectral bias. What happens is they tend to, like, latch onto simple patterns first.
Okay.
Kind of like how, like, our ears might be drawn to a catchy melody in a song before we really notice all the individual instruments.
Oh, I see what you mean, yeah.
Right.
So they're all about the big picture, but they kind of miss out on those finer details.
Exactly, and that's where SL2A INR comes in. It tries to address this bias with, well, a pretty clever solution. So instead of just feeding the AI raw pixel data, it uses these special mathematical functions called Chebyshev polynomial.
Chebyshev polynomials. Okay, you're going to have to break that one down for me. That sounds a little intense.
Yeah, fair enough. Well, imagine Chebyshev polynomials like a set of specialized filters.
Okay.
And each filter helps the AI to focus on a different aspect of the image. So, like, one filter might be really good at picking out edges and boundaries.
Right.
And then another filter might be better for, like, emphasizing textures and patterns and stuff like that.
So it's like giving the AI a bunch of different tools to analyze the image from, like, multiple angles all at the same time.
Exactly. And by using these filters, SL2A INR can, like, help the AI grasp both the big picture and those really crucial little details right from the start. And that makes all the difference.
Okay, this is starting to sound really cool, but I guess the real question is, like, do these fancy filters actually work? Give me the wow factor. What can this thing actually do?
Well, the research shows that it definitely makes a difference.
Right.
One of the areas where SL2A INR really shines is in something called super resolution.
Super resolution. Okay, is that kind of like what they use in, like, spy movies and stuff?
Where
they, like, take a blurry picture from a security camera and make it, like, super sharp?
Yeah, exactly. It's like you take a low resolution image.
Right.
And you basically enhance it, sharpen it, so you can actually see the detail that was, kind of hidden before.
So we're talking, like, CSI level image enhancement here.
Exactly.
Yeah.
And SL2A INR is particularly good at it. In the paper, they actually tested it with this standard image. They call it the parrot image, I think, and the results were pretty remarkable.
Okay, now you got to tell me more about the super parrot because I'm really curious now.
Right. So they basically started with this like really high quality image of a parrot, and then they blurred it to create this like low resolution version.
Okay.
Which
yeah.
is like a common way to test these super resolution algorithms.
Right.
And when they ran that blurred image through SL2 it was able to reconstruct a much sharper, more detailed image than any of the other methods they compared it to.
Okay, so like what kind of details are we talking about here? Like, was it able to like recreate the individual feathers on the parrot or?
It was even better than that. I mean, you could see the individual feathers for sure, but also like the texture of the parrot's beak, the subtle color gradation stuff that the other methods just like totally missed.
Wow. Okay, so this is really impressive stuff because it's one thing to have an AI that can like recognize a parrot in an image, right?
Right.
But to be able to like recreate those tiny, tiny details from a blurry image, that's a whole different ballgame.
For sure. And this level of detail, it's not just about like pretty pictures either. I mean, think about the implications for like medical imaging, for example.
Yeah.
Like a clearer CT scan could mean detecting a tumor way earlier. Or think about enhancing satellite imagery for, environmental monitoring. You might be able to spot like tiny changes in deforestation patterns that you wouldn't be able to see otherwise.
Wow, yeah. I mean, the possibilities really are pretty much endless when you think about it. It's like you're giving a magnifying glass to like every field that uses visual data.
Exactly.
This is really amazing stuff. But besides like making images sharper, what else can we actually do with this?
Well, it's not just about the quality of the results, but also the speed.
Okay.
The paper found that SL2A INR is actually much faster and more efficient than other INR methods.
So it doesn't just see better, it sees better faster.
Exactly.
That's amazing. How does it do that?
Well, remember those Chebyshev polynomials we talked about?
Yeah.
They're not just good for like extracting details. They also they make the whole computation process more efficient.
Okay.
It's kind of like having a more streamlined engine under the hood, You get better performance, but you're also using less fuel.
Wow, that's really incredible. I mean, speed and efficiency are like the name of the game these days.
Yeah.
This is starting to sound less like a research paper and more like the blueprint for some kind of technological revolution.
Well, it definitely has the potential, right? I mean, we've only really scratched the surface of what SL2A INR can do. The paper focused on a few specific applications.
Right.
But its implications could go way beyond that.
Oh. Yeah. My head is like spinning with possibilities here. We've talked about like medical imaging and satellite data, but what about like facial recognition? This could be like huge for security systems. Right?
Oh, absolutely. I mean, imagine being able to like pick up on those really subtle facial details, even in like low light conditions or from a distance.
Right.
That could totally revolutionize like security and surveillance systems.
And think about like how we store and share images online.
Right.
Like with SL2A INR, you could potentially like compress images to be a fraction of their current size, but without losing any of that like crisp detail.
Exactly.
Like imagine like browsing through your photo library and like never having to worry about storage space again.
Exactly. Or imagine streaming like super high definition videos, even with like a really bad internet connection.
Right.
SL2A INR could like totally change how we experience like the entire digital world. It's not just about AI seeing better. Right. It's about like unlocking this whole new level of efficiency and possibility in how we like capture and store and share, visual information in general.
Wow. That is a really exciting thought. I mean, it's like we're on the verge of some kind of like visual revolution or something. But with all this talk about like the potential and the possibilities, I also can't help but wonder about like the bigger picture.
Yeah.
Like what does this all really mean? Where does this technology eventually lead us? I mean, it's like we're like holding the key to a door we didn't even know existed, right? Mm-hmm. And behind that door, it's like this whole world of sharper, faster, just like more visually amazing possibilities. It's kind of mind-blowing.
It really is exciting. And yeah, you're right. This is like not just about, making things a little bit better. This technology could like fundamentally change how we experience like visual information, you know?
Right.
It's pushing the boundaries of what we thought was even possible.
Yeah. And we've talked about like all these amazing things it could do, right? Like how it could revolutionize medical imaging, make our like online experiences so much faster, so much, richer. But whenever we're talking about this kind of big technological leap, it's also important to think about like I guess the bigger picture here.
Absolutely.
So like besides, all the cool technical stuff, what are some of the I don't know, like the broader implications of this technology?
Well, that's the really important question, right? I mean, on the one hand, you have the potential for like incredible good.
Yeah.
We're talking about things like, earlier disease detection, managing our resources more sustainably. We could even have breakthroughs in like scientific discovery just because we're able to analyze, visual data with so much more precision.
Right. But I mean, on the other hand.
But on the other hand, we also have to think about the potential for misuse. I mean, like any powerful tool, it could be used in ways that weren't intended. Like imagine, for example, the ability to, enhance and analyze images. That has some pretty serious implications for things like privacy, right?
Yeah.
I mean, imagine a security camera that can not only like identify individuals, but can track their every move with like incredible accuracy.
Yeah, that is a little bit creepy.
Yeah.
I mean, it really seems like as this technology like gets more and more powerful, more widespread, we're going to have some serious conversations about, how to make sure that it's used responsibly and ethically.
100%. And those are conversations that need to happen across disciplines, right? It's not just up to like the engineers or, the developers. It's policymakers, it's ethicists. It's like society as a whole, who need to be thinking about like the potential consequences here and figuring out how to make sure we're using this technology responsibly.
Absolutely. Wow. This has been an amazing conversation. We've gone from blurry faces in our photos to like the future of AI and its impact on like society as a whole.
Yeah, it's pretty amazing the things that this kind of technology makes you think about.
It really is. It really is. And it just goes to share, whenever we're like exploring these new technologies, we're bound to come up against like these really big questions. It's like we're like peering into a microscope and suddenly we're seeing this whole new universe full of like wonder and possibility, but also like a lot of complexity.
I love that analogy.
And I think, SL2AI and R is really giving us a glimpse into like the future of AI and image representation. And one thing's for sure, this is something that's going to shape our world in some really big ways.
But we want to hear from you. What do you think? Like, what part of this technology are you most excited about? What are your concerns? Let us know. Share your thoughts, and let's keep this conversation going. And with that, we're going to have to wrap up this deep dive. Until next time, everyone, keep exploring, keep questioning, and keep diving deep into the fascinating world all around us.
All right, so imagine trying to describe like a totally amazing sunset you saw.
Yeah.
Right? You wouldn't like whip out a magnifying glass and start listing off every single color, would you?
No way. You talk about how the light looked on the clouds, the way the colors blended together, that kind of thing.
Exactly. You'd get at the essence of it. And that's what's so cool about this whole world of implicit neural representations.
INRs, for sure.
Right, INRs. It's all about how computers are learning to represent super complex stuff, images, 3D models, you name it, in a way that's, well, more human.
It's like this, think of a neural network, kind of like a program that's built like our brains are, and it's learning this smooth and continuous representation of an image.
Instead of pixel by pixel.
Exactly. It's more like having this magic formula that can just recreate the whole image just from a few coordinates.
So you're saying it can store tons of information, but in a really efficient way.
Exactly. And the best part is you can zoom in forever and you won't get that pixelated mess. It's what we call resolution independent.
Which, goodbye blurry vacation photos, right?
Mm-hmm.
This paper we're looking at implicit neural representations with Fourier-Kolmogorov-Arnold networks mostly focuses on images and 3D shapes. But this feels bigger, doesn't it?
Oh, absolutely. There's this challenge, though, that's been hanging around with INRs, and it's this whole balancing act, right? You got to capture the big picture, but then also nail all the fine details at the same time.
So, like, getting the shape of a tree is one thing, but what about, like, every single leaf, every vein on those leaves?
Yeah, that's where it gets really tricky.
And that's where this whole frequency idea comes in. I'll be honest, when I hit that part of the paper, I thought we were suddenly talking about radio waves or something.
Well, it's funny you say that because the analogy actually works pretty well. Think of tuning a radio. You need to be on that exact right frequency to hear a specific station, right?
Okay, I'm with you.
INRs are kind of similar. They need to capture this whole spectrum of frequencies within the data. So low frequencies define that overall shape, the big picture stuff, and then the high frequencies. Those are what control all those tiny details, the really fine, subtle stuff.
This paper goes pretty deep into the math behind all this, but there's this part that really jumped out at me. Their solution to this whole frequency problem, they call it FKN.
Right, the Fourier-Kolmogorov-Arnold network.
Definitely a mouthful.
It is, but basically FKN is this special kind of neural network, and it's specifically designed to help INRs grab onto those high frequencies. More effectively, get those details just right.
So it's kind of like giving your INR like an HD upgrade or something. But did they actually test this FKN thing out? What kind of results did they get?
Oh, they definitely did, yeah. The paper looks at two main things, images and then 3D shapes. For the image side of things, they took a bunch of super high resolution photos and then basically just let FKN loose on them.
To see if it could actually recreate them.
Exactly. And they wanted to see how it stacked up against all the other, state-of-the-art methods.
And how did it do? I mean, did it blow the others out of the water or what?
It wasn't even close. FKN just crushed the competition. They use this metric called PSNR. It basically measures how sharp an image is. And get this, FKN improved the PSNR by almost 9%.
Whoa, 9%. That's going to be a huge difference, right?
Oh, yeah. We're talking about a difference you can actually see, like even when you zoom way in.
Yeah.
And, it's not just about making prettier pictures.
Right. There's got to be some real-world applications for this.
Exactly. Think about things like medical imaging. Being able to represent those scans with that kind of clarity, that could be a game changer for how doctors diagnose and treat conditions.
Oh, okay, now I'm really starting to see the potential. But what about the 3D stuff? What kind of shapes were they working with?
They used all sorts of stuff, like a whole library of 3D models, everything from statues to just everyday objects. And again, FKN really stole the show, especially when it came to capturing all those little details and, just those really complex shapes. For this, they use something called IOU, which stands for intersection over union.
Intersection over union, okay.
Yeah.
And that measures...
basically how well the recreated shape, how much it overlaps with the original one.
So higher IOU means a more accurate reconstruction.
Exactly. And FKN just blew past all the other methods. I mean, it was incredible. The level of detail they were able to achieve, it was practically impossible before. It's like, imagine trying to recreate a sculpture, right? And I mean one with all those tiny, intricate details.
Okay, I'm picturing it.
Previous methods, they might get the general form right, but they'd miss a lot of those fine details. But FKN can reproduce all of that with this crazy accuracy.
That's pretty amazing. One thing that stood out to me in the paper was how fast this FKN thing seems to learn. They mentioned something about faster convergence compared to other techniques. Is that as big of a deal as it sounds for someone who doesn't speak fluent math?
Oh, it definitely is, yeah. Training these models can take a ton of time. I mean, sometimes we're talking weeks or even months, and it takes a lot of data, a lot of processing power. So the fact that FKN is able to learn so much faster, it could be a game changer.
Because you could actually put it to work in the real world.
Exactly.
So if we could do all this with the images and 3D models, what's next? What other kinds of information could we represent using this stuff?
That's the big question, isn't it? What's so cool about this whole field, about INRs, is that it's still early days,
Totally.
There's so much potential to completely change how we capture and even interact with all kinds of data. I mean, this paper focused on images and 3D shapes, but what about smell?
Smell? Wait, you mean digitally recreating a specific smell?
Exactly. Imagine being able to capture the exact smell of a fresh cup of coffee. And I don't just mean the chemical formula, but the actual sensory experience.
Okay, now that's just wild. I can already see the headlines, download your favorite scents. But seriously, if we're talking about capturing something as subjective as smell, doesn't that bring up a whole bunch of other issues?
It does. It really shows you just how powerful this technology could be. I mean, we're talking about representing basically anything with incredible precision, from physical objects to something as abstract as a memory.
Memories? Hold on. Are you saying that we might actually be able to store and replay our own memories with perfect detail?
It might sound crazy, like something straight out of sci-fi, but the potential is there. This paper, by focusing on FKN and improving the resolution of INRs, it's brought us a step closer to that becoming a reality. And it really makes you wonder, what are we going to do with that power?
That's a big question, for sure, one we can't ignore. As this technology keeps getting better, we really need to think hard about what this means, the good and the bad. It's a responsibility for all of us.
It's a brave new world we're entering, and the more we understand these technologies, the better prepared we'll be to handle, the opportunities and the challenges that come with them.
This deep dive has really been something else. It feels like we've just scratched the surface of what INRs can do, and clearly there's a ton of potential here. For anyone listening who's as blown away by this as we are, we'll link to the paper and some other cool articles in the show notes.
And hey, if any of you out there listening have come across any groundbreaking research in this area, we'd love to hear about it. Always up for diving deeper into the world of INRs.
Absolutely. Until next time, everyone, stay curious.
All right, so today we are diving into the world of AI.
Really exciting stuff.
It is really exciting and also
A little bit frightening.
Yeah, a little bit frightening.
Yeah.
We're talking about whether we can trust AI, and specifically looking at this research paper that digs into what happens when AI has to use specific information that you give it.
Right. So we're going beyond just like chat box having a fun conversation.
Right.
We're talking about when you need AI to be reliable to work with your documents.
Okay, so this is like when you're doing research.
Exactly.
You need your AI assistant to stick to the facts.
Yeah, stick to the script.
Don't go off on a tangent.
Exactly.
Make stuff up.
That's the thing, is AI doesn't always play by the rules.
Oh, no.
And this paper, it calls these slip-ups hallucinations.
Hallucinations. Okay, so my computer's not going to, start, I don't know,
Not quite.
seeing things.
No, not like that.
Okay.
When we say hallucinations in this context, we're talking about AI getting things wrong.
Okay.
And the researchers, they found that there are actually 5 types of these hallucinations.
5 types of AI errors. All right, so break it down for me. Like, what's going to happen with my AI assistant?
So 2 of them are particularly important when you're giving your AI documents to work with.
Okay.
And those are over-responsiveness and excessive refusal.
Over-responsiveness. Okay, I think I know someone like that.
Right. So imagine,
Just talks too much.
yeah, you ask a question based on your documents, and the AI throws in this extra stuff that it just thinks it knows.
Oh, like it did a Google search on the side?
Exactly, even if it's not in your sources.
Ah, that's so frustrating.
In
If you're trying to really nail down.
Right, you're trying to get it to stay focused.
Yes.
And on the flip side, you have excessive refusal.
Okay.
This is where the AI is too cautious.
Oh, interesting.
And it refuses to answer, even when the answer is right there in your documents.
So it's like it's saying, I don't know, even when it has the answer.
Yeah, exactly. And the researchers, they found that this refusal problem is a big one.
Okay.
A lot of systems out there, they struggle with knowing when to answer and when to just,
Keep quiet.
stay quiet.
Yeah.
Don't say anything.
Which, if you can't trust it to know if it doesn't know something,
Exactly.
how can you trust it at all? This reminds me, actually, I was using ChatGPT to draft an email. So I've got this AI assistant who's either giving me way too much info
Right.
or just I don't know, refusing to answer the question.
Yeah.
Not super helpful.
Not very trustworthy.
No. So how do we
measure that?
how do we measure that?
How trustworthy an AI system is.
Yeah.
Well, the researchers in this paper, they didn't just want to point out the problems.
Okay.
They wanted solutions, right?
Right.
So they came up with a way to actually measure how trustworthy an AI is for this kind of work.
Okay.
And they call this trust score.
Trust score.
Yeah.
Does it give it a letter grade?
Not quite,
Okay.
but it does give it a score.
Oh.
And that score is based on a bunch of different factors, but essentially boils down to how well the AI can figure out when it should and shouldn't answer based on what you've given it.
So can it recognize its own limitations?
Yeah. Can it say, I don't know?
Because that seems like a big one, right?
Huge.
I don't need an AI that's pretending to have all the answers.
Exactly.
When really it should be I don't know, consulting Wikipedia in the background or something.
Right. It has to know its boundaries.
Yeah.
But it's not just about staying quiet.
Right.
Trust score also looks at how accurate the AI is when it does give you an answer.
Okay.
So is it actually backing up its response
Important.
with your documents?
Yeah. Nobody wants to get busted for plagiarism because their AI assistant
Exactly.
went rogue.
Went off script.
Yeah.
And that actually leads us to another important component of this trust score.
Okay.
How good is the AI at citing its sources?
Oh, that's a good point.
Right.
Show your work.
Exactly. Just like you learned back in school.
Yes, exactly.
And this is something that some AI systems are really good at.
Okay.
Others, not so much.
Really?
Yeah, it's still a big area of research, figuring out
Interesting.
how to teach these AIs proper citation etiquette.
So, potty training a puppy But for AI.
Exactly.
Got it. Okay.
You got to teach it where to go
Yeah.
and how to cite those sources correctly.
Okay, so how do they actually teach it to be more reliable then?
So they developed this training method that they call trust align.
Trust align. Okay.
And it basically uses a massive data set
Okay.
of questions and source documents.
Mm-hmm.
But here's the key. They include examples of both good and bad responses.
Oh, interesting.
It's like showing the AI model.
Like what to do and what not to do.
Exactly.
Oh, that's cool.
So it learns to recognize those patterns,
Oh, wait.
avoid those common mistakes.
So the more it practices, the better it gets.
Oh, exactly.
They basically sent this AI to boot camp
Yeah, Trust Align Bootcamp.
to learn how to be trustworthy.
That's the idea.
But does it actually work?
That's the real question, right?
Yeah.
So they put it to the test,
Okay.
and they compared it against some of these big commercial AI systems,
Oh, wow.
ones that everybody's using.
Yeah.
And get this. The AI trained with Trust Align actually did better
Right.
at giving those reliable sourced answers.
So it actually outperformed some of the big names.
It did.
Wow. Okay, that's
It's still early days for this research,
sure.
but it's really promising to see these kinds of results.
Yeah. I mean, this could really change how we use these AI tools.
Absolutely. As these techniques improve,
Yeah.
AI is going to become even more helpful.
So what's the big takeaway here for our listeners?
I think the biggest thing to remember is don't just blindly trust AI.
Yeah.
Just because it sounds confident
Right.
doesn't mean it's right.
It could be hallucinating.
It could be hallucinating. Exactly.
Right.
So double check that information,
Always good to be skeptical.
especially in the age of AI.
Yeah. Trust but verify.
Exactly.
Well, we have covered a lot of ground in this deep dive on AI.
Yeah, we've talked about hallucinations, trust score, trust align.
It's really fascinating.
It is, and I think it raises even bigger questions.
Yeah. What happens when we start asking AI to be creative
Exactly.
or insightful?
What are the ethical considerations then?
Yeah, how do we measure trustworthiness when it comes to those more subjective tasks?
Exactly.
That's a whole other deep dive.
Absolutely.
Okay, yeah.
Well, on that note, thank you so much for joining us for this deep dive.
It's been a pleasure.
And until next time, stay curious.
Ever wondered what happens when you mix music with artificial intelligence? We're going to be diving into that, exploring a pretty big development in AI music.
It's a really exciting time, for sure. AI is already changing music, but there are some big questions about copyright and where it's all going.
Totally. On the one hand, AI is making catchy tunes, maybe even hits. On the other, you've got artists worried about their work being used without asking. It's creativity versus copyright. But we're going deeper than that, looking at a potential solution, a new data set called PDMX for ethical and legal AI music.
Right. PDMX, the public domain music XML dataset, it's kind of a dream for AI developers, music people, anyone really. Imagine 250,000 pieces of public domain sheet music, all ready for AI.
Okay, before we go too fast, let's explain for those who aren't, AI music experts. We're talking sheet music, not recordings, right?
Exactly. That's important. A lot of AI music generators use recordings. They try to copy the sounds. But PDMX, it uses symbolic data, the actual notes, rhythms, everything, in music XML.
So teaching AI to read music theory, not just mimic.
You got it. Music XML is like a universal language for computers and musicians. AI gets to understand how music really works, the melodies, the harmonies.
I see why it's a big deal. But why public domain music specifically?
That's the ethical legal thing. Existing data sets, they often have copyright problems. Licensing is unclear. But PDMX, all public domain, so copyright free. No worries for developers.
A giant free buffet for AI music makers.
Basically, it's huge. Developers can push what AI can do musically. No legal fears.
Makes sense. But with so much music, isn't there a risk of, well, not all public domain music is good music?
You're right. The PDMX creators knew that. Just having tons of data doesn't equal good music, so they made sure the data set was high quality.
Now, that's interesting to me. How do you teach AI about good music? You can't just say, Beethoven's better than this polka.
Right,
Yeah.
not that easy.
Yeah.
They used, you could say, the wisdom of the crowd. They looked at user ratings, comments from MuseScore, where a lot of the music came from, so they could focus on music people actually liked, thought was well made, not just any old cheap music.
Smart. Give the AI a head start on good taste. But even with that, 250,000 pieces of music, there's got to be duplicates. How'd they deal with that?
Yeah, huge problem in data science, especially with music. The PDMX team, they didn't mess around. They built a whole system to find and handle duplicates.
No way they had people checking every note, did they?
Huh? No, that'd be crazy. They used, get this, AI. They combined a bunch of techniques, one's called text embedding, to analyze the titles, even the musical content itself, for similarities.
Wait, AI looking for duplicate sheet music? How?
Think of it like turning song titles into math, capturing their meaning. Beethoven's Symphony No. 5, Symphony No. 5 by Beethoven. Similar, even if the words are a little different.
Okay, but the music itself, how can AI tell if two pieces are basically the same song?
Like a musical fingerprint. They
What?
compared notes, rhythms, all the elements, see how much they match. Of course, no system's perfect, so experts look things over too, make sure they were removing actual copies, not messing with unique arrangements.
AI and humans teaming up for quality control, nice. But did it matter? Did the AI make better music with the good data? How do you even judge that?
The big question. And yeah, big time. They did tests, trained AI on different versions of the data set. Some got everything, some got the good stuff, curated, no duplicates, highly rated.
Okay, now I'm really interested. So what happened? Did the good music AI actually do better?
It's really cool what they found. The AI trained on the better data. Not only was the music objectively better, like followed the rules of music more, but people actually liked it more too.
Whoa, they had people listening to AI compositions, judging them. That's wild. So even AI needs good influences. Clipchamp's approach seems like it worked.
Definitely did. It changes how we think about AI making music. It's not just giving it tons of data. It's about the quality, the variety, just like teaching a person.
It's like, that saying, garbage in, garbage out. Applies to AI too. Bad data, bad music. Good data, good music. That's promising.
Yeah. And it's what's exciting about this. We're not talking about replacing composers. It's about tools for anyone to make music, be creative.
I like that. Making music easier for everyone. Songwriters, film people, game developers.
Right. Imagine working with AI to make melodies, harmonies, even orchestrate your song.
Yeah.
So many possibilities.
This is exciting stuff, but right now AI is mostly happening at big companies. PDMX is open. Anyone can use it. How does that change things?
That's important. PDMX is open source, copyright free, so it's fair. Anyone can experiment with this. No huge costs, no legal worries, more diversity, more new ideas.
AI music for everyone, not just a few. I like that future. This whole deep dive, really interesting. We went from AI copying songs to maybe helping anyone write a symphony. All from public domain sheet music.
Shows what happens with open access working together. Who knows what music will come from this?
Exciting and kind of mind-blowing. And listeners, if you're as fascinated as we are, check out the PDMX dataset yourself. We'll have links.
You might discover something new, get inspired.
On that note, we'll wrap up this deep dive into AI music and PDMX. Until next time, keep exploring, keep making music. Okay, get this. We're diving into the world of robot parkour.
Robot parkour.
You heard right. Robots doing parkour, like actually leaping and flipping like you see in those online videos. Sounds like something straight out of a sci-fi flick, huh?
Definitely does. Sign me up.
And that's what's so cool about this deep dive we're doing.
Okay, so what's the source material for this one?
We're looking at some seriously cutting-edge research, a paper called Agile Continuous Jumping in Discontinuous Terrains. Pretty dense, full of equations and jargon, but don't worry.
Yeah, that's what we're here for. Break it
Yeah,
down.
exactly. We're going to break it down and pull out the mind-blowing stuff. Because what these researchers have accomplished is, well, let's just say it's going to change how you picture robots.
Okay, I'm intrigued. No more clunky robots bumping into walls in the lab.
Nope. We're talking about robots moving with, get this, animal-like agility through unpredictable environments, no less.
All right, now you're just messing with me. What kind of robots are we talking about?
The star of the show is the Unitree G1 robot.
Unitree G1 rings a bell, but refresh my memory.
It's a relatively small robot, but don't let that fool you. This little guy is the real deal. Like, in this paper, they had it climb a 14-step staircase. That's twice the height of a standard staircase, right? And it did it in under 5 seconds.
No way. Twice as fast as a human could.
At least. And it wasn't just some carefully controlled lab experiment. This was out in the real world, with all the unexpected bumps and inconsistencies you'd expect.
See, that's always been the challenge with robotics. Getting them to work in a pristine lab is one thing, but the real world is a whole other beast.
Totally. And these researchers, they knew that. They were incredibly meticulous in how they bridged that gap between simulation and reality. Like, they went to great lengths to replicate every tiny detail of the robot's hardware in their simulations.
Hold on, back up. So they're teaching this robot to do parkour.
Essentially.
How do they even begin to do that? It's not like they just hand it a skateboard and say, go for it.
Right. It's a surprisingly systematic process, almost like how we learn complex movements, but with a robotic twist. Think of it like this. They created a system with a scout, a strategist, and an athlete, all working together in perfect harmony.
Okay, now you got to break that down for me. Who are these scout, strategist, and athlete?
So the Scout, officially called the height map predictor, it's basically the robot's eyes, uses a depth camera to constantly scan the environment, creating a 3D map of the terrain ahead. Just like how our eyes judge distances and help us avoid obstacles.
So it's constantly building a picture of its surroundings, figuring out what's where.
Exactly. But then the question becomes, okay, what do you do with that information? That's where the strategist comes in.
It's a strategist.
Yeah.
And that's the part that figures out the moves.
Yeah.
The strategist, or motion policy, to use the technical term, it's the decision maker. It takes all that 3D map data from the Scout and uses it to, well, strategize, figures out the best way to navigate the terrain.
So is it like plotting a course through this 3D map, making sure the robot doesn't stumble or take a wrong step?
Exactly. But it's not just about avoiding obstacles. It's about doing it with agility. The strategist decides everything. How often to take a step, how much to move each leg, how fast to go.
Wow, so it's like a choreographer for a robot dance-off, but instead of dance moves, it's parkour.
It's a great way to put it. But here's the real kicker. It learns all these moves through something called reinforcement learning.
Reinforcement learning, okay. You're going to have to break that one down for me. Is this where they download parkour moves from robot TikTok or something?
Huh. Not quite, though I'd love to see that TikTok. No, imagine training a dog with treats, right? You reward good behavior, and they learn what gets them those tasty snacks.
Okay, I'm with you. So the robot's getting virtual pats on the head for every successful move.
Exactly. They set up this whole simulated environment, kind of like a virtual obstacle course. The robot gets to practice its moves without any real-world consequences.
Oh, so like a robot training montage, falling down and getting back up until it nails that perfect parkour move.
You got it. And with each success, the algorithm reinforces those successful movements, and over time, it becomes incredibly good.
I got to say, it's kind of inspiring, this little robot pushing its limits and learning from its mistakes, all in the name of science. But we're not just talking about virtual hurdles here, right? It actually pulled off these feats in the real world, which just seems next level.
You're right, and that's where the athlete part comes in, the leg controller. This is the part that takes the strategist's plan and translates it into actual physical leg movements.
Wait, so it's coordinating all those joints, the timing, the balance. I can't even imagine the complexity of that, especially at high speeds.
It's incredibly complex,
Yeah.
especially when you think about landing those jumps, maintaining balance. It's like a symphony of robotic motion.
Absolutely mind-boggling. But they didn't just assume this virtual training would work seamlessly in the real world, did they?
No way.
Mhm.
Remember how we talked about how meticulous they were? They replicated every tiny detail of the robot's hardware in their simulations.
Didn't they even account for things like, what was it called, motor saturation?
Exactly, motor saturation. That's when you push the motors to their absolute limit, like a weightlifter attempting a personal best.
Yeah.
They wanted to be sure the robot wouldn't try something in the real world that its hardware just couldn't handle.
Such incredible attention to detail. No wonder they were so successful. But this begs the question, what does this all mean for our listeners? Why should they care about robots doing parkour? Well, put yourself in a scenario like, say, an earthquake. Imagine a robot that can scramble through rubble, way faster than any human rescue team ever could.
Right. Getting to areas that would be way too dangerous for us.
Exactly. It could be a game changer for disaster response.
Uh-huh.
First one on the scene, assessing the situation, maybe even bringing supplies to trapped survivors.
I can see it now. Robot medic coming through.
Seriously. And think about it, it's not just disaster zones. Construction sites, factories, even just navigating your own house. I mean, picture a robot bringing you that thing you left upstairs.
Instead of yelling up the stairs, honey, can you grab that?
Right. The possibilities are pretty mind-blowing.
No more climbing that ladder to get to the top shelf, that's for sure.
Exactly. It's like the future of home convenience is a parkour robot. But on a serious note, the applications for various industries are huge.
Absolutely. Though some people might be thinking, oh, great, robots taking over even more jobs.
Yeah, I get that. But, it's not necessarily about replacement, right? It's more about, augmentation, helping us tackle challenges that we could never even dream of handling on our own.
Exactly. Humans and robots working side by side, playing to each other's strengths.
Now that's a future I'm all for. This research is amazing, but it sounds like they're still figuring things out. What's the next step? What's next for our robot friend here?
So right now, most of the robot's movement is, forward, backward, up and down. Think of it as like a two-dimensional plane.
Okay, so no breakdancing just yet.
Not quite. But that's what they're working on, expanding its range of motion so it can twist, turn, move side to side.
So true parkour with all the fancy flips and
Yeah,
stints.
exactly, giving it that full freedom of movement. Once they crack that, who knows what we'll see.
I can't even imagine. It's really mind-blowing stuff. Well, there you have it. We've taken a deep dive into the world of robots doing parkour, learned how researchers are teaching machines to move with, like, almost human-like grace and agility.
We broke down the three-part system that makes it all happen. The scout that sees the world, the strategist that plans the moves, and the athlete that actually pulls it all off.
And we even got a taste of reinforcement learning, where robots basically learn through trial and error, just like us.
And we can't forget about those real-world implications. From disaster response to everyday life, this technology has the potential to change a lot.
It really does. If this is where we are now, just imagine what the future holds for robots and humans working together.
The possibilities are endless.
That's right. Thanks for joining us on this incredible deep dive.